I told you na. इसको एक कॉमन करो, इसमें ऑडियो जाना चाहिए.
इसमें ऑडियो ओके. There is no audience.
But I won't be comfortable going that way.
I am also. Okay, keep both at the middle. I will
But
be.
I have to come like this, ma'am.
I have to come like this.
No, that's not good.
Uh,
And to read also, it's not comfortable.
Okay.
This is fine.
keep it a little bit low.
Then I.
Then high. Then it will. So it will. Hello.
I have to press that.
Good morning, everyone. Good morning, respected dignitaries, guests, faculty members, students, and all the participants. I, Annapurna Pradhan,
I, Deepak Bandakavi,
PhD scholars of NIT Rourkela, welcome you all to the inaugural session of the Wireless Antenna and Microwave Symposium 2022 organized by IEEE. Now I request our student volunteers to escort the dignitaries onto the dais. Please. Thank you, sir. Thank you, ma'am.
Now I request the volunteers to present the flower bouquets to the respected dignitaries.
Volunteers, please come forward.
I request the audience to join your hands, please.
Thank you. Shubham karoti kalyanam, arogyam dhana sampada, shatrubuddhi vinashaya, deepam yoti namastute. Now I request all the dignitaries to light the auspicious lamp for the occasion. I request
Now we request all the dignitaries to please arrive at the lamp. I also request all the audience to rise for the occasion.
माता सरस्वती शारदा हे माता सरस्वती शारदा विद्यादानी दयानी दुःखहरिणी जगत जननी ज्वाला मुखी माता सरस्वती शारदा हे माता सरस्वती शारदा कीजे सुदृष्टि कीजे सुदृष्टि सेवक जान अपना इतना वरदान दीजिए तान ताल और आलाप बुद्धि अलंकार शारदा हे माता सरस्वती शारदा हे माता सरस्वती शारदा हे माता सरस्वती शारदा. Thank you.
I thank all the dignitaries. And thank you, audience. So now I request the General Chair of Wams 2022, Professor K.R. Subhashini, to address the gathering. So please welcome ma'am.
A very good morning to all of you. As a General Chair, Wams 2022, I would like to welcome the dignitaries, the faculty colleagues, NITR students, delegates and participants who have traveled across the globe and who joined virtually. A warm welcome to all the guests. NIT Rourkela is very fortunate to organize IEEE sponsored Wireless Antenna and Microwave Symposium, first of its series. WAM's idea was conceived during February 2021 with the dynamic and motivational leadership of Dr. Sudhakar Rao and the enthusiastic team. The symposium is successfully launched. Coming to the technical details of the symposium, we received 265 technical papers covering 3 tracks, wireless, antenna and microwave. The accepted papers are 176, distributed for oral and poster sessions. The 4-day symposium is embedded with a lot of technical events such as young professional talks, student activities, women in engineering, along with the oral and poster technical presentations. I would like to thank the sponsors, IEEE, APS, Quartzon, Altair, and Triple Technologies, Professor Dr. Sudhakar Rao, for giving a good sponsorship for making this event a grand success. I conclude my note with a very big thank you and appreciation for the student volunteers who are working tirelessly for the past few days to gear up this event. I would like to express my sincere appreciation to our director, Professor K. Uma Maheshwar Rao, head of the department, Professor D. Patra, faculty colleagues and different units of the institute who are involved in organizing Wams 2022. And remaining technical aspects will be shared by our executive chair. So thank you all and a warm welcome again to NIT Rourkela.
Thank you, ma'am. Now, I request Professor Pradeep Sarkar, Director in Charge NIT Rourkela, to address the audience. Sir, please.
Chief guest Dr. Christopher and Dr. C.S. Rao, our chair, executive chairs Sudhakar Rao, Dr. Sudhakar Rao, General Chair Professor K. Suhasini, Head of the Department, Electrical Engineering Department, Madam Dipti Patra, and distinguished guest of the dais, participants, delegates of the symposium, my faculty colleagues and students, very good morning to all of you. Our director, Professor K. Uma Maheshwar Rao, is on leave, and I am representing him in this event today. It's really a great pleasure to welcome all of you to our campus, NIT Rourkela campus, for the inaugural program and for the 4-day program of the Symposium on wireless antenna and microwave technologies. Our institute, NIT Rourkela, is, I want to tell a couple of information about our institute. It is one among the top ranked engineering and science institutes of our country, and probably the largest among the NITs in terms of student strength and the programs that we offer, and also the size of our campus. And also we are one of the first generation NITs, and this institute completes 60 years very recently, last year, of service to the nation. And our goal is to excel in research and development on those areas which supports the society in general and our nation in particular. So the theme of this symposium, that is wireless antenna and microwave, very well falls within the goal of this institute. With these wireless technologies have already brought a lot of benefits to the societies and our nation. A mobile phone in everyone's pocket is a simple proof of the contribution, societal contribution of this technology. And I see very rapidly this technology is evolving from 4G to 5G, and I am now hearing that it is moving towards 6G. So this technology has a lot of potential to grow further. My association, I have been into this wireless technology in a indirect sense 15 years back. I was associated with AT&T to structural design the antennas, the communication towers, where you mount the antennas. So there is an airport in Texas, Killeen Airport. I think all the towers, communication towers, 15 years back was designed by me as part of Bechtel Corporation, who got the project from AT&T. But on those days I did not enjoy the communication technology that well. But today, as a civil engineer, we see our construction management completely depends on the communication, wireless communication. So nowadays we don't do brake test to check the strength of the concrete. We get information through the sensors which are mounted inside the concrete, gives us the progress of the strength in our mobile phones, and when to remove the scaffoldings, when to go to the next sequence of the construction. Everything comes from the wireless technology. So we are getting benefited hugely from wireless technology. Not only that, see, when tunneling, in metro rail tunneling, there are sensors. Before making the tunnels, they put sensors and see what is the pressure coming, whether the tunnel will collapse or not, and based on this information they are doing the construction. Despite that, still there are some problems in recent Kolkata metro. So there are ample opportunity to grow further in this technology, and if this technology grows, the society, country will benefit. So I am very proud that some of our colleagues have taken the initiative to collaborate with IEEE, which is a very renowned society globally, to organize this symposium. And my best wishes to the Executive Chair, Professor Dr. Sudhakar Rao, Madam Suhasini, K. Suhasini, and the entire team of this symposium. I wish this symposium a great success. Thank you very much.
Thank you so much, sir, for those wonderful insights. And next, I invite Dr. K. Sudhakar Rao, sir, Executive Chair of Wams 2022, to address the gathering. We are privileged to have you, sir. Thank you.
Sir, please.
Good morning and welcome to Wams 2022. I hope you are as much excited as I am to attend the Wireless Antenna and Microwave Symposium and learn from the experts, keynote speakers, and other colleagues. So this is very exciting time. A lot of planning went into this work, as Professor Subhashini Ratna told. So this is almost 18 months of planning. I think the seeds for this were planted during one of the workshops chaired by Dr. Subhashini. That was a long time back. And now you can see the tree has grown up very beautifully. And then now it is first time giving the fruits. So let's all enjoy the fruits of Wams 2022 tree. Wams is a multidisciplinary symposium or conference covering not just one track. I think there are a lot of conferences which cover antennas, microwaves, and some maybe antennas and microwaves. But this one focuses on wireless communication technology and associated antenna and microwaves as well. So this is not just one area. So it basically tells that to develop any product, you need to have a knowledge in all these areas. For example, wireless communication system, satellite system, cell towers, any communication system, whether it is for aircrafts or satellites or drones or missiles. I think this wireless communication system is very important, and as somebody said before, I think wireless is growing. I think we talked about 4G, 3G, 4G, 5G, and now 6G. And actually, in US, we're working on 100G. So you can imagine the demand for the capacity of the communication system. It's growing very exponentially for certain applications, not all commercial applications, for some military applications as well. So these are interrelated fields, all three of them. So I think if you're a student, I think you should learn all three fields, maybe more, mechanical engineering and manufacturing as well, to become a good engineer rather than just studying in one area. I think understand the other areas as well. That gives a broad perspective, and you can become a good engineer when you grow up. So there is a need for such a conference because no other conference covers this wide areas. So we thought that there is also a need for a low-cost conference. Most of the conferences are held in big hotels and with a lot of registration fee, and people from the industries and academic institution professors can go, but student cannot afford to go. So the focus of this conference is mainly students and young professionals. So that's how it's a low-cost conference, and we organize a bit differently compared to other conferences. So this is different in many areas, Wams 2022. So like I said, its focus is mainly on students. So I think its idea is to train the students and make them interested in working in communication areas, either it's antennas or microwaves or wireless communication systems. Several travel grants are established. I think anybody who is eligible, I think they'll get a grant. So they can travel, they can free travel, and they can come to the conference. And also we are providing free accommodation to the students, giving accommodation in the hostels. So that's also very good. You don't need to pay for your stay. Like I said, it's a low-cost conference with a registration fee roughly about half of what other conferences have. Like if you're a student, I think you need to pay only about 3,000 rupees or something for 4-day conference. So that's very low. And it's planned to be held in educational institutes rather than in big hotels and big conference halls. So the idea is to sort of attract the students and also the faculty as well, to train the faculty and get them interested. So these are held in NITs, for example, and IITs and other educational institutions. Other unique thing about this is the website and all the conference activities are managed by the students, not conference planners. Typically, conference planners will charge anywhere between 6 lakhs to 8 lakhs for their fee, but all the website management, you can see the registration office, travel grants, everything is managed by students. And thanks for all the student volunteers for making this happen. Finally, there's no other conference has so many awards as this conference. We have 18 awards for best papers and other things. So typically, even the flagship conference, IEEE APS has around 8 or 10 at the most. So I think this conference is mainly, most of them I think allocated to students and young professionals. And thanks to all the sponsors, I think we have almost about 3 lakhs of awards money. So thanks for all the sponsors. They're all volunteers or established people from ESA and outside, and India as well. Thanks to Dr. C.J. Reddy, thanks to Clancy Leo, thanks to Nazar Chahat, thanks to NNSS R.K. Prasad, thanks to Surendra Paul, and many other volunteers who basically contributed to the sponsorship money. It is encouraged that all students become IEEE student members. So there is a student booth actually. So you can go and sign and register, and you get the first year's membership fee free. That's paid by the conference. So become a student member, and then I think continue to become the member, and it pays a lot of dividends in future. I think once IEEE is, it's actually a career, it boosts the career quite a bit because you network with other people, other experts, and then involve in IEEE. So then you can become members, senior members after 10 years. Then if you do good work, you can become fellows and life fellows as well. So now I like to thank few people. I like to thank Professor Subhashini Ratna for her excellent organization of Wams 2022 as the general chair. So she is a live wire, and handled difficult situations with a smile and a quick wit. Always no short of bits from her, so you have to be always ready when she speaks. This could not have happened without her dedication, hard work, and passion, and leadership as well. Thanks to Professor Saifur Rahman, IEEE 2022 President-elect and 2023 President, for accepting to give the inaugural address through pre-recorded video, in spite of his busy schedule. I'd like to thank Professor Umama Rao, Director of NIT Rourkela, for providing its facilities free of cost. Thanks to Dr. I have to say here, the two stalwarts here. Maybe people may not know, especially students. One is Dr. S. Christopher. So he is the ex-DRDO chairman and scientific advisor as well for Defense Ministry. I know him very well, his work. He also did PhD at IIT Madras. So he's the one single-handedly changed the entire defense capabilities, especially for low-cost aircrafts, combat aircrafts. I think under his leadership, I think many aircrafts were built, and many people don't know, but he's an excellent researcher as well. So he is now retired from DRDO, and he is continuing as taken up a position at IIT Madras as a professor. The second stalwart, I would say, call him as my friend, C.S. Rao. So he is the CEO and president of QuadZen. It's a multinational corporation. It has branches in US. I think head office is in Bangalore. I think he has thousands of employees. And he has done a lot of projects, mainly for Ministry of Defense and other institutions as well, mainly on upgrading the wireless communication systems with 4G and 5G, especially for northeastern areas and other projects as well in USA. Both of them are actually very good engineers, very good students. That's how they started. Very good researchers. That's how they developed. And now they are very good, very well-known leaders in their respective fields. So I think learn from them how they have grown their career, and I think follow some of the advice I think they'll give later. Like to extend my thanks to technical and financial sponsors, Custom Microwave Inc., Dr. Clancy Leo, who is also a close friend of mine, IEEE APS, Antenna Propagation Society, QuadZen, IETE, IEEE Kolkata Section, IEEE Student Branch Chapter Rourkela, DRDO, Interpol, and Altair. This could not have happened without their sponsorship, both the technical and financial sponsorship support. Also, I'd like to thank Professor Ramana Reddy for helping with many activities, including TPC, designing the brochure, mementos. He's the awards committee chair, and he designed the award plaques, session schedule, everything. He's Mr. Everything. Special shout out to all the student volunteers who worked very hard over the last 1 year, not just working on website, but also all the, today you have seen the design of the stage, and everything is managed by them, the website, etc. So I want to end my address with a quote. Criticize an old person because you know what he or she has achieved, but don't criticize a young man because you don't know what he will become in future. So there could be many of you here, students. So there could be a J.C. Bose, a C.V. Raman, a Vikram Sarabhai, or an Abdul Kalam among these students. So my advice to you is study well, learn from your professors, learn new things. Don't be afraid to expand your horizons. Work smart and not hard, but work smart, and make your parents and the country proud. Thank you.
Thank you very much, sir. Now we have privilege to request the guest of honor, Dr. S. Christopher, to share few words with us. Sir, please.
Dignitaries on the dais, professors, students, and participants. Good morning. It's indeed a pleasure for me to. So the mic is there. Hello. Hello. Yeah. I would like to thank the organizers, particularly Dr. Sudhakar Rao, who triggered me to come over here. And I was very much pleased to be here because I heard about him much more as a senior. One side I was a bit afraid that meeting a senior, he may rag me. Of course he did. So he called me that I'm a senior because I'm a grandfather, right? So likewise, we had our good time, as he was telling that the most often that we learn from the peers rather than necessarily from the professors. I'm not saying that we are not going to say anything or tell you something, but the peers also teach a lot. Pandemic has taught us many things, to be in isolation but still get contacted through virtually. However, my experience while teaching in IIT Madras found that the students, while we take the class, were finding it difficult to listen to and then try to understand because of the situations. Not all of us are having independent, separate house and room for us to keep ourselves isolated from the rest of the chores of the house and then listen to the professor and understand. And it became more obvious when we were insisting for the tests and exam, we have to proctor them, and so we asked them to keep your mics on, both as well as the sort of a video or video set, particularly videos on, so that we can monitor them or see them. During that time, I could encounter there are several events happening in the background, and I wondered how they could have really did good studies. I was 8th student in IIT Madras with my professor, M.S. Narasimhan, and I think Sudhakar Rao was the 3rd, and we missed narrowly by an year or two by the time the overlap was not there. I have seen most often, we all sit for the tea and try to talk, obviously about the professor start with, later on technical things, and most of the technical things we really enjoyed because sharing from one to the other experience. We all started in GTD, and when he said today, Kunjamena and Padak, the same paper was given to me also. So we have got a tradition of learning and going more and more. And GTD was a fundamental thing we all learned basically there. Over the years, I find antennas, particularly in the case of radar, we had 20 years back a good discussion. Computers catching up close to the antenna, maybe in between some photonics may come in, but the antennas cannot be replaced. The sheer reason why the space allows the microwave to be used as a wonderful tool or a transmission line to reach out to many people. So the antennas will remain. The other side, digital will catch up as much as possible. Like in the case of most of the modern radars, we call them digital radars because right at the IF, even before the IF, we would like to digitize it and use it. So the antennas is going to remain same. But as Dr. Sudhakar also was telling, the product is becoming more interdisciplinary. You cannot be associating yourself only with a very narrow area of antennas and be done with that. If you would like to be a productive, useful personnel in your own domain also, interdisciplinary is essential. So maybe in my keynote address also I'll try to bring in one of the antenna that what you have developed, how the other things have helped. As regards ourselves are concerned, I virtually followed Dr. Sudhakar Rao from the probably MTech Converse in IIT Kharagpur, followed by IIT Madras, then landed up in LID. Then of course he's smart enough to, he said smart rather than hard work, and he did a smart job of going abroad. I stayed put here. Okay, no regrets. Notwithstanding that, in all those days in IIT Madras, whatever we learned, we utilized some way or the other in our own work. I was sharing with him, they did in those days phased array radar, the first of its kind. We used to use Ferrite phase shifter, and it was of course imported from Boyd, Professor Boyd or Dr. Boyd from US. But then the mechanism by which they could analyze and finally what we call it is collimate, in the sense when you have a plenty of elements, first phased array when it is done, there will be a mutual interactions as well as its own inherent phases will be different. So if you have to bring them to the same phase level, that is called collimation. So the way in which they adapted in those days, really I admired the lessons I learned from them. We have only a far field, and if you have a uniform array, obviously in the far field, if they are all in phase, you will get the maximum gain. But if you have 1,000 element out of that, even 500 becomes collimated, the rest of the things not collimated also, you will not see much difference in the gain. So how do you make all the 1,000 of them to be in the same phase? So they get into the subarray technique and they move the subarray. So with the number of limited elements being considered at any given time, so you have to be in phase, at least those 4 of them. The next 4 of them are combined, something like that. They did it, and it was a very, very wonderful idea to think in those days, about 20, 30 years back. Followed by that, they also found that only amplitude looking is not the best way. You look at the difference pattern, that means the phase. Then you will see a contrast so immediately that you are able to find out and make it more and more elements to come in line with the same phase. So that was the case. After he left, I got into another soup because they have done a very good job. So we have to force ourselves in a much bigger array. So the array size from nearly about a meter, it has become 2.5 meters, weight-wise less than around 100 kg was expected, but it was slightly more, they expand. When we did in C-band, it was 4 tons or so. We could not go and use the same, the far field range what they've used. So we have to create our own test setup also. We did that. And ultimately, the fruit of the thing is now, today the Akash array or Akash system, which finally after several years, I started in 80s or 90s. And when I was a secretary, I could, honorably hand over to the defense services. That was a proud movement. So the time period for a product takes so much of time, and sometimes we have to do everything ourselves. Likewise, slotted array is another area when we worked, and we used to learn from IIT Madras using the linear programming, you solve the transcendental equations. And the laptop, whatever we had was a 20 megabits was the hard disk itself we can imagine. So we had to push it and store it in the floppy and put back and all those things. Of course, we started in IIT Madras with the punched cards was our work started. So there are several learning. All the time trying to tell is, you put your hard work now and you will get a bonanza. And what Dr. Sudhakar Rao was telling, that we are all like a ladders to be there for you to step on us and go forward. So I would like to end with a small story. There is a boy who was in a hotel or some sort of a coffee shop he was working, and he was not found to be happy by an elderly man who regularly came there for coffee. One day the elderly man started asking him, "Boy, why you are unhappy?" "Sir, I don't have money for my own, coming up in life." So he thought that he will help him out in some fashion, so that he will be happy in the future. So he gave a gold coin and then a couple of gold coins and said that use it, and whatever you would like to do and come up in life. So he's so happy that somebody has given him, and he was found to be happy for a few more days. But after 3-4 days later, he was again unhappy. What he did is, because it's such a precious, So the man could not control himself. He asked him, "What happened? Why you are happy yesterday and all? Today again unhappy?" Then he said, "Yes, sir. You gave me something, I was happy, but now I lost it, so I'm not happy." What do you mean by lost it? The gold coin was so precious to me, so I took it and nicely buried it in the garden. And every day morning I'll go open that pit and then see whether it is there. It was there. So it was such a confidence it was giving to me. But then one fine morning, somebody watching me that he has taken it out. So my point is, or the point at the time that conveyed is, the gold coins are the opportunities and avenues given to you by professors, by your parents, by elders, and so many others. Please make use of it, use it. Don't bury it and keep it. You will be the best person in the world. Thank you very much. Bye.
Thank you, sir. Thank you so much for that inspiring story. So now we have the privilege of having another guest of honor, Dr. C.S. Rao, sir, to address the audience. Please, sir. Your presence is an honor, sir.
Dr. Sudhakar, he was also with me in IIT, we are all from the same IIT Chennai. He was doing esoteric work when I was simply doing some simple MTech, and he was doing in those days one of the most advanced in those days that was felt. So we always used to look up to him. And meeting him here is a real pleasure. Dr. Christopher, a very well established and very well recognized and great job that he has done in DRDO. Professor Subhashini, ever active person. I didn't know that she is from my same hometown that I came to know today. And Professor Sarkar, Professor Deepthi, and all the volunteers, students, participants, professors, faculty, Professor Harish, who came from all the way from Kanpur. Nice to meet you here. It's a pleasure to be associated here. I won't take much time, but basically I would like to say that it's a conference that when Dr. Sudhakar told me that Wams 2022 was getting organized here, I felt that I should be associated with this for a simple reason. My first engineering admission that I got was in Rourkela, Regional Engineering College in those days. And lo and behold, I came, joined, but I left in 1 month. Because so then I went to other colleges because I couldn't continue here for whatever health reasons. So it brought back me memories when I started way back in 70s, 71, I think. So it's a great bond, maybe it's destiny. So I came here again at the end of my professional career at the age of 65 now. So it's nice to be here. Thank you. I just wanted to say wireless, Y gig era is where we are here today. And in this Y gig era, the technologies that are playing a big role today is Wi-Fi 6 and Wi-Fi 5, going to Wi-Fi 7, 5G, LTE, and also the satellite constellation-oriented internet access and mobile broadband to all of us. So these are the 4 technologies that are playing a significant role. So that these technologies are having so much of an impact, as Professor Sarkar was mentioning. What we used to get the internet from access from a digital subscriber line and a pair of copper wires coming to our home has moved to cable broadband, fiber to the home or coaxial cable, to the mobile, to right now where the satellite internet access is happening. So we have really moved from an age of an industrial age, which used to be around 100 years, to an information age, which has compressed this to 50 years, to the invention age, which is all around AI, ML, and cloud, which may be about 10 years. And all these technologies like 4G, 5G, Wi-Fi 5 or Wi-Fi 6 or Wi-Fi 7 are all having a decade of life from one technology to another technology. So why gig era of broadband is all about coexistence of different spectrums of different technologies with carrier aggregation, what hitherto we have not seen and felt and heard, but the technological revolution has enabled, irrespective of the frequency band, irrespective of the mode of transmission of TDD or FDD, the carrier aggregation can take place, and you can realize a 1 gig RF channel width, so as to give you the bandwidths and band throughputs on the air interface, which could be n times gigabit. So that's why I call this as a Y gig era of broadband. To this now, Elon Musk, we all need crazy people, and he is one such guy. Like Dr. Sudhakar did a lot of crazy things for US defense. I only wish he had contributed enough to the Indian defense so that we wouldn't have had the attacks from Chinese. So the Elon Musk has added satellite broadband around 42,000 low Earth orbit satellite constellation in Ku and Ka bands for 100 Mbps around LEO satellites, and also a steerable motorized antennas that are there on your rooftop, unlike what you see today, which is a Tata Sky or some such thing, which is a fixed antenna. So you will have a steerable antenna towards the orbit, and thus what has truly evolved is a true coexistence of terrestrial network and a non-terrestrial network to give you the feel of wireless gigabit broadband access. What used to be a few decades ago is RF channel of 200 kilohertz has now reached a 2 gigahertz RF channel. Number remains the same, 0.2 or 0.02, 200 kilohertz to now it is 2 gigahertz of RF channel width. Nobody could have imagined, and that's what Dr. Christopher was mentioning, where the technological revolutions taking place with the imagination, innovation, and where we are heading. It offers a great opportunity for the youngsters to take this forward without questioning the influence of these technologies on the society. As Professor Sarkar mentioned, how great an influence of mobile technology has made in our day-to-day lives. No one expected the path link or path budget or air interface between a mobile and a base station to have n times gigabit air interface throughput. And fundamental to all these technologies, fundamental to all this revolution is only two aspects. That is the antenna technology. Without an antenna radiating, general purpose technology on the phased antenna arrays, adaptable antenna arrays, and today it's called what used to be a simple passive antenna has become active, adaptable active antenna systems. With beamforming, not in 2 dimensions, beamforming in 3 dimensions. So with that beamforming technologies, I think which is likely to be each one of us in our handset will get a beam dedicated to us from a radiating point of presence called BTS. And these BTSs are also now changing from what used to be a single all-in-one base station to a distributed base station to even base stations which are being put as a aerial base station for some large venues and meetings. So there are and IEEE has tested, one of the papers which I read is about aerial base station. There's a separate, complete special issue has come out about aerial base station and UAV and all that. So that is the kind of revolution taking place. So Y-gig era is also moving towards what we used to see at a point of presence used to have 200 Mbps or 300 Mbps, starting from 20 Mbps in 3G era. And today it is maybe n times 2 gigabits at every point of presence. And where we are, in a given square kilometer, you may have 10 terabytes, 10 Tbps per square kilometer is the order of magnitude of the capability of the radio network delivering a mobile broadband service to each one of us. The antenna array size, 10 log to the base 10 m, m is the order of the array, and the antenna arrays have gone to 256 by 256 MIMO capable antenna arrays are coming up, which is creating a huge spatial diversity, and hence the spectral efficiencies that we have not heard of has now reached 10 bits per hertz also, and antenna gains that we have not heard of has come to varying from 6 dBi antenna gain. Today it may be 36 dBi antenna gain, which in turn is increasing the power that is required to transmit could be quite high. So these are the types of innovation that are taking place, and you are all going to see an excited telecommunication, wireless arena going forward. That's why the conference is very aptly named as Wireless Systems around 4G, 5G, Wi-Fi, what have you, 6G, and antennas, which is a very essential thing around adaptive antenna arrays, MIMO systems. In this, we need to feel proud, to see the contribution of some of the proud Indian sons. Jagdish Chandra Bose, which Dr. Sudhakar was mentioning earlier, is the person who invented 60 gigahertz way back in 1896. And I happened to give a lecture on the same IEEE organized by IEEE in Bangalore on his 150th birthday. And today, that 60 gigahertz invention way back in 1896 is playing a significant role in millimeter wave communications for backhaul as well as for access. And we'll all see the LAN that you are used to seeing in your labs, offices, which is a 1G LAN or a 10G LAN, is now going to be a 60 gig wireless LAN. And see what the forefathers and the proud Indian son way back has invented. And that's what Dr. Christopher was mentioning about Dr. Boyd. I mean, these are the luminaries. And similarly, another person who has played a significant role is Professor Paul Raj, Arogya Swami Paul Raj of Stanford University, who is who has been inducted into the National Inventors Hall of Fame in the US. And who are there in the National Inventors Hall of Fame? Most of you may know. If not, go and check it out, especially for youngsters. I'm saying this. The person who invented the bulb, Edison, the person who invented the aeroplane, Wright brothers. And these are the kind of people who are in the National Inventors Hall of Fame. And Professor Paul Raj was inducted into that for the simple reason that he has invented a general purpose technology called MIMO, which is today a biggest antenna technology and around which this conference is being held. And without that, we wouldn't have been getting the mobile internet speeds at what we are experiencing today. And so added to this, the software engineering and software is moving to a significant era. Open source boom is happening. AI ML is going to play a significant role in the propagation modeling, channel estimation, coding theory and its impact on the communication channel for the S by N. I think all of you have got a great opportunity to combine the effects or combine the power of computing and software onto the wireless systems knowledge and become thorough professionals. We are going to see and channelize all these enablers of technology. I would only say will create probably a digital resonance for all the young minds of this era, thus having a digital literacy for all the hinterland and urban India, from class 6 students to class 10 students with a laptop enabled with a 5G or a 6G in the near future, which we call it as a digital future, around a digital infra of all these great technologies of 5G, 6G, and antenna technologies, and wish this world to have a very bright Y-gig and high-performance computing era with photonic ICs becoming a reality. No more a silicon ICs. Good luck. Thank you very much for the organizers to give the opportunity. Thank you.
Thank you very much, sir. Now, we will have the inaugural address by Professor Saifur Rahman, IEEE President-elect 2023, Founding Director of the Advanced Research Institute at Virginia Tech, USA, where he is the Joseph R. Loring Professor of Electrical and Computer Engineering.
Hello everyone, I am Professor Saifur Rahman from Virginia Tech. It is my pleasure and honor to serve as the 2022 IEEE President-elect. I would like to begin by thanking Dr. Sudhakar Rao, Wams 2022 Executive Committee member,
for the invitation and the opportunity to speak to you today. And I applaud all of
This should not happen for 2 minutes at least.
across academia, industry, and hello everyone. I am Professor Saifur Rahman from Virginia Tech. It is my engineering and scientific professionals working across academia, industry, and government who have a desire to learn, collaborate, and give back to their community. IEEE brings together not only engineers but also technologists, industry, from the fields of computer sciences and hello everyone. Technology, I am Professor Saifur Rahman from Virginia Tech. Biological and medical sciences, engineering, mathematics, and scientific professionals working communications, academia, education, industry, management, law, and have a desire to learn. One of the greatest choices that I made was to become involved in IEEE. It helped me to define who I am, both personally and professionally. IEEE is centered on our members and volunteers who create the value of IEEE, guide the organization's direction, allow IEEE to have such a strong impact on the world, and fulfill our mission to advance. Hello everyone. I am Professor Saifur Rahman from Virginia Tech. It is my pleasure and honor to serve as the 2022 IEEE President-elect. I would like to begin by thanking Dr. Sudhakar Rao, Wams 2022 Executive Committee member, for the invitation and the opportunity to speak to you today. And I applaud all of the organizers' efforts in putting together this event. Your agenda for these 2 days is very impressive. You have created a unique platform for students, young professionals, and faculty members to network, learn, and engage with one another. For those who are unfamiliar with IEEE, we are the world's largest technical professional society. Our members are in 160 countries, diverse, vibrant engineering and scientific professionals working across academia, industry, and government who have a desire to learn, collaborate, and give back to their community. IEEE brings together not only engineers but also technologists from the fields of computer sciences and information technology, physical sciences, biological and medical sciences, mathematics, technical communications, education, management, law, and policy. One of the greatest choices that I made was to become involved in IEEE. It helped me to define who I am, both personally and professionally. IEEE is centered on our members and volunteers who create the value of IEEE, guide the organization's direction, allow IEEE to have such a strong impact on the world, and fulfill our mission to advance technology for the benefit of humanity. It was my experience as a member that encouraged me to devote my time and energy to IEEE, and I know that every volunteer I meet values being part of our community for a long time. I hope that as university students, you have the opportunity to interact with your local IEEE student branch, which can help you advance your education and get your career off to a good start. Participating in your student branch can help you develop leadership and interpersonal skills that are essential for building a rewarding career. Student members can also participate in regional workshops, conferences, and competitions, including student paper contests and scholarships. IEEE Young Professionals, which encompasses all members from recent university graduates to experienced professionals and entrepreneurs, is a highly diverse international community of enthusiastic, dynamic, innovative members and volunteers working to evaluate their career goals, polish their professional image, and create the building blocks of a lifelong and diverse professional network. As students and young professionals, you may hold a different perspective regarding the value of membership and how you want to participate in a membership organization. At IEEE, we are always looking for opportunities to improve how we engage with our members, and we want you to take on the roles and responsibilities that matter to you. As technology continues to reshape the world we live in, the energy, innovation, fresh perspectives you offer are essential. We're living in a challenging times. There are shifts in workspace structures, moves to virtual workplaces, more globalization, and the convergence of multiple and diverse fields of interest. Our IEEE students and young professionals who can lead cross-functional, cross-sector, cross-cultural initiatives, you will be the leaders who will address technology's toughest challenges while bringing rewarding careers. You will be the leaders whom others follow and emulate. Whether your focus is on aerospace or microwaves, computers or energy or AI, there is a community for you within IEEE. Within IEEE, you will find like-minded people engaged in work of a similar nature. You will also find different perspectives and approaches of tackling the grand challenges each of us encounters in our particular discipline. You'll find young women and men like yourselves just starting to explore their passions within our professions, and active engineers currently working in industry, in government, and in academia, and retired professionals with a wealth of acquired knowledge to share. IEEE is an international community that is truly unlike any other. There's no group on the planet that is driving more advances in technology across the widest breadth of fields and disciplines than IEEE. As a person who believes in the power of technology to benefit humanity, I find that concept of true diversity and inclusion to be a very compelling vision for our shared future. Before I wrap up, I would like to wish all of you the greatest success as you move forward with what I'm sure will be challenging and fulfilling careers. get involved, volunteer, be an active participant, whether it be with a professional association, humanitarian efforts, or continuing education. It is your future. Build it. Thank you very much.
Thank you, sir. Now, I request the dignitaries to inaugurate the souvenir. Sir, ma'am, please. Middle. Let's have a huge round of applause. Thank you, sir. Thank you, ma'am.
I request Professor Pradeep Sarkar, Director in charge of NIT Rourkela, to present small tokens of appreciation to the dignitaries Dr. C.S. Rao and Dr. S. Christopher, sir. Let's join our hands.
Come back. Thank you, sir.
Thank you, sir. I now request Professor Deepthi Patra, Head of the Department, Electrical Engineering, to give the vote of thanks.
Esteemed dignitaries on the dais and off the dais, the Executive Director of Wams 2022, Professor Sudhakar Rao, our guest of honors, Dr. C.S. Rao and Dr. Christopher, our Director in charge, Professor Pradeep Sarkar, and General Chair of Wams 2022, Professor K.R. Subhasini. Off the dais, I'm finding my senior professors of the department and also the institute, and Professor Harris from IIT Kanpur, all the delegates, the student participants, the student volunteers, the faculty members, and all the staff members and who are behind the successful of this inaugural session, and as well as they will also organize the other events. I warmly welcome all of you to the inaugural session of Wams 2022. Though the climate is very peak summer with a mixture of humid. We never had thought while it was incepted by Professor Sudhakar Rao and informed by Dr. K.R. Suhasini, we never had thought that it will be possible at NIT Rourkela and organized by Department of Electrical Engineering in physical mode. But finally, it was possible due to able guidance of Professor Sudhakar Rao and Professor K.R. Suhasini. I really appreciate and put my sincere thanks to both of them for this successful event of Wams 2022. This platform will definitely provide a lot of opportunities to the young professionals, to the students, the research scholars, and also the faculty members and industry sectors to share their expertise in the domain of wireless technologies, antenna, and microwave technologies. As already the stalwarts have already told about lot of things for WAMS 2022, and I have nothing more to tell, but as a head of the department, I want to introduce my department to the international forum. The Department of Electrical Engineering was established in 1961, and it is one of the premier departments of NIT Rourkela. It imparts knowledge and in the domain of electrical engineering, and not only in electrical engineering but also the interdisciplinary sector. We have one BTech degree in electrical engineering and also 4 MTech specializations that includes power electronics and drives, power systems engineering, control system and automation, and electronic systems and communication. And we have lot of I can tell that advanced research laboratories, including the other laboratories, because in the domain of electrical sciences, our faculties, they are doing research in various domains that includes all the sectors of electrical sciences. So antenna, microwave, wireless technology, they are all of one of them, and in these sectors we have number of faculty members who are doing research in that domain, and also Professor K.R. Suhasini is one of them, and who came forward to organize this event. So on behalf of electrical engineering, I sincerely thank to all the student volunteers, to all the participants, to all the people, the IEEE, who are IEEE professionals who are behind this organizing of this event. And also, I sincerely thank to the sponsors, because without that, it would not be possible. And as Dr. Sudhakar Rao told that it is a low cost, this event could be possible with a low cost. And it was open to mainly for young professionals and the student research scholars. So definitely I hope that it will give a good platform for them to share their knowledge, and as well as we looking forward that these people will definitely will go ahead getting lot of tips, like we can call that lot of knowledge, not only knowledge but also how to use those knowledge in the social sector. So all the best, my best wishes to all the participants and also to the volunteers. Definitely, because of them only, we could make it possible. Thank you, all of you.
Thank you, ma'am. Now, I request Professor K.R. Suhasini ma'am to present a token of gratitude to the dignitaries. Thank you, ma'am. Now, I request our student volunteers to escort the dignitaries off the dais. Thank you, sir. Thank you, madam. Thank you, all the participants and volunteers for organizing this one properly. Now, I request everyone to have their high tea, which is arranged outside, and I request the volunteers to escort the dignitaries to the place. Thank you, everyone. Please have it. Then we will gather after that for our next keynote talk.
So it will be a break of 10 minutes. Please have your high tea there, and we shall be back by 10 minutes. inaugural session. Okay, we can start.
We can start.
If they had good refreshment, something like that, we can. No? Okay, fine.
Sir, to sit down.
Okay.
Then we will start.
Madam has to come. They can further tilt the screen. Or it's fine. No? Zoom.
Let madam come inside, then we'll start. Okay.
Yes.
They are providing UPS backup to this. So that's why this needs to be turned off after they provide the UPS backup, and then it can start.
No, sorry, was asking to
We can put it after one top. One
They are
top.
done already. They are done already. Email.
Tell sir that we are this backup. It takes 2 minutes.
Yes, ma'am. You have to.
Welcome back everyone to the post-inaugural session. Our first keynote speaker for today is Dr. S. Christopher, Professor IIT Madras, ex-chairman DRDO and Defense Secretary. Dr. S. Christopher served as Secretary Department of Defense R&D and ATVP Chairman DRDO, BrahMos and ADA from 2015 to 2018. Prior to that, he has served in Bangalore-based DRDO labs, LRD and CAPS for 27 years in various capacities, including founder, program director and the chief designer of the prestigious Airborne Early Warning and Control System or AWACS, well known as NETRA, which successfully served in the recent Balakot airstrike. During his tenure as the Secretary Defense R&D, NETRA was inducted into the services, which placed our country in the selected group of 4 nations in the world having this facility. He was instrumental in the induction of the nuclear submarine Arihant and the fighter aircraft Tejas into service, which again brought India into the elite group of countries internationally. Several other DRDO designed products were also inducted, to name a few: torpedo, Varunastra, decoy, Marichi and sonars under his leadership. Further, many DRDO technologies TOTs were given for production. The overall cumulative order value given to DRDO jumped from 1.45 lakh crore over 57 years to 2.71 lakhs crore during his 3 years of tenure. Dr. Christopher has several patents and copyrights to his credit, is the author of several publications and has won several prestigious awards, including Scientist of the Year Award in 1998 itself. Now, after retirement from MOD, he joined the faculty of IIT Madras as a professor in Electrical Engineering Department and is pursuing research on an ambitious and futuristic photonic radar. He is also the chairman of the AIDAT. I welcome Sir to present his talk. Please, sir.
Sir, we have a column mic. You can stand there and column mic and pointer and column mic. Come on.
Thank you very much. And once again, let me thank the organizers for giving this opportunity. Before I start my talk, let me request for the video to be played.
Presenting and C India, the Indian Airborne Early Warning and Control System designed and developed by Defense Research and Development Organization DRDO, with Center for Airborne Systems CABS as the nodal agency. DRDO is the research and development wing of the Ministry of Defense under Government of India and has 52 laboratories all over India. Center for Airborne Systems, located at Bangalore, has the core competence in the areas of airborne systems, command, control, communication, computer and intelligence, surveillance and reconnaissance, C4ISR, and aircraft system integration and flight testing. The AEW and C India has capabilities for surveillance, communication and electronic warfare, effectively making it a true force multiplier. The primary sensor of the AEW and C India system is the Airborne Active Electronically Scanned Array AESA-based primary radar PR for detection and tracking of targets in surveillance coverage defined by the operator. The electronic scanning ability provides faster updates on the targets with adaptive beam scheduling and has capability to compensate for the aircraft roll through electronic beam stabilization. The AEW&C system detects and tracks targets in air-to-air and air-to-sea surface modes. The airborne radar has enhanced surveillance range and has capability to detect low-level targets and the targets masked by terrain as compared to that of ground-based radars. The secondary surveillance radar, SSR, or the Identification Friend or Foe IFF system interrogates the targets in the surveillance volume and processes the replies from the transponders of the targets to declare it as friend or foe. The SSR augments the primary radar and is an IFF Mark 12 S system capable of interrogating in modes 1, 2, 3A, 4, C and S Level 2. The Active Antenna Array Unit AAAU of the AEW&C houses the electronics of primary radar and secondary surveillance radar. AAAU, engineered structurally to meet the FAR 25 requirements, consists of Transmit-Receive Multi-Modules TRMM as the primary building blocks, antenna panels covered with a cladded radome. The Electronic Support Measure ESM on board the AEW&C India intercepts the electronic emissions in the surveillance volume and determines its direction of arrival with high accuracy to provide the electronic order of battle to the mission operator. The AEW&C system intercepts, monitors and analyzes communication signals and estimates the direction of the emitter. This is achieved by the Onboard Communications Support Measure CSM. The mission system integrates the sensor data from the PR, SSR, ESM and CSM to form system tracks providing kinematic and tactical information by identification and classification of tracks. The Airborne Early Warning and Control System assesses the threat and declares the threat level to the operator. Based on the threat level and operator inputs, the system provides battle management solution to scramble fighters and control the fighters through the interception mission and recovers back to the base. The situational awareness of the operator is provided on the Operator Workstations OWS as Recognizable Air Situation Picture RASP during the mission. The OWS acts as the interface between the AEW&C system and the mission crew. 5 front-facing operator workstations configurable to any of the mission modes, that is, Air Situation Picture ASP, Command and Control C2, ASP and ESM, ASP and CSM, Onboard Training OBT, Image and Voice and Global Air Situation Picture Recorder gives the agility to the mission crew to switch from one mode to the other as per demands of the operational scenario. The mission computer, which is the heart of AEW&C, controls all the sensors and orchestrates functions of all the mission systems in an integrated way. The system has a Self-Protection Suite, SPS, consisting of Missile Approach Warning System, MAWS, sensors of which are located to cover the entire threat volume, a Radar Warning Receiver, RWR, with a full 360-degree coverage, and a Countermeasures Dispensing System, CMDS, capable of dispensing chaff and flare to evade from radar-guided and IR-guided missiles. The Mission Communication System MCS of AEW&C system has a set of 5 VUHF sets for air-to-air and air-to-ground communication. The MCS facilitates air-to-air VUHF voice communication between the AEW&C mission crew and other fighters and intercommunication on board among mission crew and flight crew. The AEW&C operates in radio relay mode, facilitating communication between two entities located beyond their range capability. The AEW&C system has the capability to communicate with multiple ground exploitation systems (GES) through a line of sight LOS C-band data link and a beyond line of sight KU-band SATCOM data link. These data links provides facility for the operators to transmit data and communicate over two voice channels in full duplex mode for communication by onboard operators with ground operators located at GES. The GES acts as an interface between the airborne early warning and control system and the ground control stations of user. The GES displays the air situation picture transmitted from the AEW&C onto operator workstations. The GES is transportable and field deployable as per the needs of the user. The system also has the capability to undertake search and rescue missions. A mission planning and analysis station provides capability to generate mission parameters data and store in a removable media which is loaded to the mission system on board the aircraft. The operator training station provides facility for training of mission operators and provides an environment for the instructor to evaluate the trainees. The subsystems of AEW&C meet the environmental specifications for transport class of aircraft as per standard and are manufactured with stringent quality control and will be certified by the Military Certification Authority (CEMILAC). System has been extensively tested at lab and the test and integration rig. Automatic Test Equipment (ATE) supports in carrying out the O-level maintenance of the system. Mission Software Support Facility (MSSF) caters for the maintenance of software upgrades. The AEW&C India is based on an Embraer 145XR executive jet platform from MS Embraer, Brazil, and is operationally very cost-effective. The aircraft is structurally reinforced and modified to integrate the active antenna array unit. The aircraft is modified with in-flight refueling capability to provide enhanced endurance to meet operational requirements. The mission systems are seamlessly integrated on the aircraft to provide capabilities which is first of its kind on this class of aircraft. The airborne early warning and control system, glory to the Indian sky, with its modular design can be adapted to meet the requirements of any country in the world through international cooperation and collaboration.
In the meantime, what you've seen in this video is the glimpse of airborne early warning and control system, otherwise known as Netra. Even in the Balakot exercise, this was used. It totally indigenously developed, yes, barring some of the electronics, particularly chip we don't have, but otherwise most of the things are designed and developed within the country. My focus in this talk is to bring out in a complex system of system where it comes to antenna, how it becomes a multi it's not confining to one discipline. We need to tackle various disciplines, and then only a fruitful product can be made for application like this. So I've taken this as a case study. It's basically an active array, and active arrays are well known in the radar system for quite some time. Presently, active arrays are used in a very, very simple way, almost every other place. In your states, periodically you've got active arrays. Thereby, the cost of the active arrays has come down, because once you need in a large quantity the chip makers are also able to do wonders in costing. So the technology sort of migrated in a radar system where it is needed for various reasons, and I will explain, to a communication system. That's where we have a spatial way of controlling the beam only to the selected or a wanted place. Thereby you get a spatial gain. That the antenna gain is not provided by the power, but it's just converging the image towards only one direction. Next slide. Oh, can I make a question, please? Yeah, sorry.
ये लाइव स्ट्रीमिंग हो रहा है
And the speed we control, so it misses. Yeah, that's the one I want. Basically, this
Excuse me.
system.
Sir, you can also put this one, sir, for the live streaming part, sir. They will.
Okay.
Thank you.
So basically the main antenna, there are several antennas. As a matter of fact, this system has got about 79 sensors. Most of them are microwave antennas. And out of that, the most important and the critical one is the one at the top. We call it as a dorsal, like a fins in the case of a fish. So that's the most important thing. Okay. The exploded view, I just thought that how it is built. It is you have a structural frames, about 11 stations are there. Then you latch on to that your antenna. In this case, we chose to have a slotted array, and we also converted from the then available model to, in our case, we also used it as a structural member itself. That means antenna is not performing only its job of microwave energy being focused or given in a particular direction, but also we are trying to use it as a structural member also. Thereby, one advantage, weight reduction. The other advantage is, yes, we have a volume constraint. If you keep on build it up and make it bulkier, it is going to have a what is called, not the weight alone, but even the size will have what is called the drag. That means you have consequently the less number of hours of flying. For a given fuel and given weight, you got some endurance, but if you increase the drag, your endurance still comes down. So that's the problem. So you have a multiple, sub-units or subsections are made in a mechanical way. Ultimately, it has to perform electrical EM performance, whatever we ask for. There are several assumptions that we make, like it should not have a ground plane or a ground plane extended or something should not be there. Most of the things will look like a violation, but it's not necessarily. Fortunately, electromagnetics also tolerant, I should say. So we have to analyze them correctly, use them properly, then you will be able to achieve what you want. The front side and the first side is no doubt it's a hood, it's non-metallic, but then we have to metallize them because you are going to have most of the time they will go through the clouds and then charge will be there. If you don't discharge effectively those charges in a proper way to the ground is nothing but the body of the aircraft, you will end up burning the TR modules, that is transmit receive module, which has got electronics there. They will simply fail. They are not very tolerant big tubes. In those days, AVAX was there. AVAX even today it is there. It is producing a 1 megawatt of power. This is having only a 65 watts of power, but number of them trying to give about kilowatts of power in that. So the basic thing is you have to protect those even in this ESD part of the charges from the clouds. So likewise, I will keep explaining to you more of the problems. Then you will understand that how innovation or the group of the team of people worked along, we could put in more and more knowledge or innovation. Because at the end of this exercise was over, when we asked what are the innovations, most of the youngsters could not explain because they looked at it as a sort of a routine work. Then I need to prime them saying that this is where we did something, this is where we did something which is new, which is good, and that's how we could achieve the overall performance. So the structural element of the array itself, the slotted array itself used as a structural element is one of the innovation. As you can see in the side, completely the modal analysis, mechanical modal analysis was done to ensure that the antenna is performing within that level of requirement. You see that the whatever the picture here, it is not looking straight. The aircraft will go through constraints. One is called the natural self load, other one is wind load or the air load. The air loads are not going to be constant. There could be a pocket of clear air turbulence and so many other cases will happen. In all those cases we should study. As a matter of fact, we have thousands of critical cases, not a one or two. There are occasions where we analyze and found only way to succeed is do a thorough analysis of all the cases, to experiment only the selected few cases. That's how we could do that. So if you open, let's say the antenna part of it, the radiating element part of it, if you open, the whole thing is an antenna. If you radiating element, if you open, kilometers of RF cables are there, and they are all weighing heavy, and we must try to minimize the weight. Right? The gentle feeling is that from the TR module, if you take equal length, it's supposed to be giving a broader bandwidth. Generally, we don't have a phase corrections needed. Thereby, squint will not come. We know all those issues. But then, with the differential length, that means from the TR module, there are 8 elements are there in a vertical direction. Likewise, 160 of them are in the horizontal direction. When you are feeding from a given TR module, which has got 16 ports, 8 for one side, another 8 for other side, there is a switching in between the two. They cannot be with the equal length cable if you would like to make them very short and lightweight. So we did that, but then you will suffer in terms of electromagnetic phase tracking has to be done over the frequency band, which we did some calibration and put it inside. That is another way of achieving some weight reduction. Ultimately, when you start the design, yes, electromagnetic design is one part. We need to start with what is the aerodynamics, in the sense aerodynamic load that is going to come. That will come from the experience or the years of flying of the aircraft. They will give you this aircraft over this period likely to experience these are all the load, and this loads will not happen every day. It may happen one day, but in spite of that, that one day also we should take into account. That means the antenna's design starts with safety first, then the performance. So in order to do that, you collect all the data and have them as a information for a structural design. That is more important. While we did the structural design, they came out. We have got 2-3 labs are there. Finally, it was made in cabs. Earlier, when it was done in another lab, the weight was expected to be about 1.5 tons max, but it was coming to be around 2.5 tons. So naturally, if you give more importance to the structural part, you may land up in a heavy weight and probably perfectly all right, no meandering or whatever it is from its shape, but then it may not even fly, or even if it flies, instead of 5.5 hours what is flying now, it may fly for 1 hour, 2 hours or 3 hours. So that is the reason we have to be very critical and optimum in that. Then the radome itself, we have got in the electronic side, what type of technology to be used. Radome, there is a huge explanation coming as a separate slide, I will tell you. We have an option of going for an independent radome, sandwich radome, or we can have what is called cladded radome. We chose cladded radome against what is at that time internationally available. The reasons for that I will tell you, and what we gained also I will tell you down the line. And MMIC chip, we are using it. Today we have got an entire TL module as a single chip. But we were not having at that point of time. We have a discrete phase shifter attenuator or a core chip having only a phase shifter attenuator and probably LNA and otherwise power amplifier. So we now have entire receive channel and the forward channel for transmission within a chip, and that too in silicon itself we can do it instead of going for a gallium arsenide or a nitride, which is much more cost economy. So we did at that point of time with the discrete and MMICs and embedded technology as far as the digital portion is concerned, because right in the array itself we have got a lot of processing also done. you can do it in the bottom or in the inside the aircraft. But when you transfer, you have to increase or remember that number of data that what you're bringing is much larger, and there could be a corruption as well as the weight penalty was there. So we transferred most of the load to the within the array itself. It has got its own good and bad, but we felt at that point of time that's the best. And coming to the mechanical, we need to apply both statics and applied loads. And there is another important thing is shock and impact. The vibration is supposed to be normally there. Whenever there is a differential pressure or whatever it is in the air, you will have some sort of a vibration. In addition to that, the shock is something which when the pilot lands, he is supposed to land not more than 1 g of landing g force. But there are some pilots, they'll come and drop. Why they do is, it could be practice, but some of them do say, but in a slippery runway, unless otherwise you do the drop, the aircraft is likely to meander and then probably it will go out of the runway itself. Whatever it is, as and when we land in a higher G, it will have an impact on all the electronics. After all, you have soldered and they can come off the soldering and so many things can happen. So we need to know that and work back on your design of the chip as well as on the boards and its vibration level and what it could magnify and what it could happen, we need to study. Another set of environmental information, like for instance rain. We always protect our antennas, even the weather radar, if you take nice cover or nice radome is there. Whereas in this case, you are having the entire array and also you are having some sort of an air inlet which will have definitely water particles. So your entire electronics is likely to get sprayed with water. So we need to find out how to take it, except for choking, totally soaking inside the water. If it can be managed, why not? And if there's a water stagnation, one part is it stagnates, the other part is they get frozen while it is flying. Maybe the further cooling and other things will get blocked. So we have to have a mechanism by which drain it. That's another study we have done. The lightning, after all, you are having all the electronics and then one is, I said, normal charges. In addition to that, lightning is much more higher way of discharge of electrical energy. During that time, you must imagine these electronics will have either a primary or a secondary type of disturbance. When I said primary, it will have a puncture, there's a hole, so many things will happen. If it is secondary, physically it look fine, but indirectly the chip will not work. So we have to take care of that. Fortunately, the waveguide selection, I mean the slotted array selection, being a metallic body, and when I said the front and back I metallize, though it is a non-metallic, sorry, when I metallize, it becomes completely a cage, a metallic cage. Thereby you have a protection against this type of lightning. We cannot simply do it and forget it saying that everything will be all right. We have to do an experiment of various things. We did. Fortunately, we have some provision in Bangalore. We did and we could succeed. And the other aspect is the temperature. Temperature, when we say, oh yes, in the ground, you'll have some higher temperature. When it's flying, it can go to -40, -50 regularly. It is not only in the summer or winter. Regularly, it can go up to -50 also, or even beyond. And in addition to that, the deployment pattern in the case of services, they would like to operate even from, let's say, somewhere in the very hot spot near the, our hottest possible regions. In which case the numbers given was even plus 71 degrees, you must imagine. So that is a type of variation. And when we are having a dorsal or the antenna on the top, you cannot put an air conditioner and keep it in the cushion. They said the entire aircraft may be in the tarmac for hours together in the hot sun, then it will be utilized. So this is the temperature you should anticipate. Inside temperature will be more. There are lots of conditions that we need to analyze and see that we are able to take care of it. Last but not the least is icing, because anywhere when your moving body is there and the cold temperature is existing, conducive for formation of the icing. If the velocity of the, whatever the air comes in, makes a near zero, delta V by delta T becomes zero, that is a place it will form ice. and we have got a scoop of opening for it to cool, air cooled we have used it. When we are doing that, there is a possibility entire opening will be closed. So for that sake, if you make the opening larger and larger, you will end up having more and more drag. So it's a question of a tricky situation. And other one is the power supply. The power supply is that if you are carrying at the voltage what is really required for the TR module, you will end up in carrying about 1000 amps plus of current, which can result in huge arc and probably the safety hazard. Your certification people will not probably permit it unless otherwise you make lots of improvement on the way of conducting or taking the power there. Plus imagine you want about 5 volts and you generate at the bottom and take it all the way maybe about 10 meters of length. By the time it goes and reaches there for hundreds of amps or even more than that, even if it drops by 0.1, 0.2, 0.3, you will get into some sort of an uncertainty. So best to have what amount of stabilization you have to do at 1000 or hundreds of amps with a 5 volts within a 0.1, 0.2 volts is going to be very, very difficult. So we took up a DC voltage of 200 volts and then later there itself we managed the rest of the generation, thereby the current is brought on. But even in the generation of 200 volts, we could have used for a conventional 400 hertz generated power to conventional isolation transformer followed by step down transformer, then the rectifier sets. These three combination would have again weighed at least 3 times what the way that we have done. We used 18 pole auto transformer, eliminated the zero tap and the center tap, and then saw to it that we have only taken the power point. The center tap elimination is a bit critical in the sense that is having a potential, though it is supposed to be zero, it is not zero in this case, 135 volts it was there. So we have to be careful that even the center port is properly isolated. Any problem happens in the power supply, first thing it will get shorted to the body in turn will go to the rest of the body. That means entire 50% of the voltage will get shorted. So we have taken care of that and we succeeded it. Of course we have done enough of experiments, up and down failures, and ultimately achieve whatever we want. And the EMIMC issues are very, very critical because it's not only our problem. You should not land up, making the aircraft into any flight critical or the safety critical issues. So that's why the issues have come. There are a number of antennas, not only for the AWNC, but also for the normal flight itself has got number of antennas. Intercommunication, interchanges, they are to be controlled. The other side is again, air cooling. We decided that we will not go for a water cooling. Normally in a TR module to remove the heat, best to go for a water cooling. But then if you do that, for the given aircraft, the size of the aircraft is small. We are not having a 707 like whatever the US has got, or whatever the AVAX has been bought by India itself from Israelis was IL-76. They all start with a huge amount of 200 tons of fuel and land up with about 10 tons of reserve fuel, whereas our aircraft we start with only about 7 tons of fuel and we land up with about 600-700 kgs of fuel as a reserve fuel. Still our performance wise, if that is 6 hours, we can get about 5.5 hours. More or less we get a performance equivalent to that, except in the forward and the rear region, because antenna cannot see, antenna is blind in those regions. Likewise, the bird impact analysis. We never think in terms of your own antenna is being bombarded with some sort of a huge heavy weight on and off or expected to be made, whereas we need to take care of those aspects. And the condition there is, yes, you can have bird hit, you will have bird hit in some time in the lifetime of the aircraft. During that time, what should happen in the condition is, you cannot have any impacted portion, part of it, coming not more than 200 grams. That is coming from, again, engine manufacturer. Engine manufacturer Rolls-Royce says, my blades can withstand maximum of 265 grams of part from your, from the dorsal, because at the velocity at which the aircraft is moving, even that can have a good impact and probably the impeller can get broken. So that's the reason we have to decide that. So we have to do a lot of design and iterations, mostly in the analysis. Finally, 1 or 2 experiments we have to do to control that. the other tolerances and maintainability. Maintainability is one of the major issue because the services will say that there is always a possibility of things going wrong and we must be able to do it fast. When we look at the antenna, this antenna is going to produce huge power. In spite of that huge power, there has to be a communication links which is existing and it will work. Existing is from the aircraft, and we are going to have several operators sitting inside. They would like to control a fighter because they are supposed to be a flying sort of a control room for the pilots. So the pilots in the hot pursuit with the enemy, at that time his communication cannot get stopped, and neither you can afford to stop your radar because the enemy is totally depending on you. Your fighter is totally depending on you. He has switched off his radar. He is operating in the silent mode. Then only he can go to the far near region of whatever your enemy territory is. Under that condition, he is solely depending on you. Your radar functioning is essential. Your communication is essential. So you do not know which antenna, which element will be utilized. There are several communication antennas, and as you can see, some of them is just below the dorsal itself is there. So you must look at the combination of all of them, what could be the effect and how to use them and what frequencies are tolerable. We got 3-4 parameters to play around. Frequency, other one is in terms of timing, the last one is spacing. So the initial design is going to be spacing, then we have to manage only with the frequency and time. So even if it has to be managed with the frequency and time, one has to study and give that entire list as a package, as a software, as a sort of intuitive advice to the operator, then only you will select. We never made everything automatic, we will give as an advisory. But anyway, those spots what he can use comes as a table and he selects one amongst them because of secrecy or whatever it is. They don't want to give us the full right to select ourselves. So, but at the same time that has to be done. So that means enormous amount of analysis as a multi-antenna analysis, and from the high frequency to low frequency, we need to analyze them and see one to the other what couples and how it couples. And if it is to be eliminated or minimized from the antenna part of it, how do we do? Have we come across any problems? Yes, we did. And what is the issue of a small aircraft versus big aircraft? Yes, we can say big is beautiful. Naturally, in this case, they are spatially separated antennas, so it is beautiful as far as the design is concerned. When you are having a smaller, the small is cute, but at the same time, you have a problem of a coupling much more. So we have a problem when we are operating in S band. There is a radio altimeter working in C band will get affected. It'll keep saying that you're ground, you're going to break or you're going to kick or whatever it is. It'll keep shouting, saying that you are flying low, which is not true. So the basic point is it is a harmonics affecting. So you have to have a sort of a control on our frequencies. It could be a filter, it may not be necessarily antenna, but most of the time antenna is also a filter. We can always ensure that right in the beginning itself we neither send out or get in, because every time if you put it on the source alone cannot generate. There are various stages, mixing happens. Even without our knowledge it happens. So consequently the frequencies are generated. So if antenna can also be a part of a filter, it can do a good job. So we had this problem, and being a ICAO standard, they will not change in that radio altimeter. It would have been very easy to put out a filter for our frequency, spot frequency. They said no, that is supposed to be a standard. We should be able to have any equipment fitted in, so that cannot be touched. So left with no other choice to add or do something. Ultimately we achieve whatever we want. Then the basic point is, why should we go for airborne? The difference between a ground-based radar and an airborne radar itself, okay, all this problem, whatever I explained, comes because it's an airborne. But in the airborne advantages, you see the coverage. The red one, when you elevate it, the antenna is able to cover a large region. Whereas if it is in the ground, you will have certainly something missed at the low flying. So this is a game between the fighters as well as the radar engineers. When you like to have the sort of evasive way of operating, they would like to fly it at as low as possible. Whereas we cannot lift the ground-based radar or put on a tower as high as what it can be done in a aircraft. You can always look at a static balloon. It was also used. The first shot will be that balloon will go by your whatever the balloon or because it's not mobile. So the AEWNC likely to stay for a longer period because of this advantage. So then naturally we have to go for this one. Already the existing types are there. There are two types. One is that your E3 and E2. They are all conventional beam, the sense that a huge slotted array giving a single beam with a very low side lobe is existing. Whereas the present, that is called, we call it as a MBA, that is in the sense we have got microwave beam forming. In addition to that, turboprop is there as well as the jet is there. Turboprop is used whenever a short runway from the aircraft carrier they use it, whereas the prop is used for a long run and long haul for a long endurance. The MBA versus ASA, you know very well that the microwave beam forming, if you ask today also AWACS people, they say the picture is very clean. Side lobes are much, much lower. If you design the side lobe for a 40 dB, irrespective of any direction, 360 degrees, you rotate your antenna, that pattern remains constant. If you have an electronic scanning with a phased array, when you scan, let's say plus minus 40 degrees, you are better off. When we stretch it to, let us say, plus minus 60 degrees, certainly your beam broadens, main beam. In addition to that, your side lobe also gets perturbed. So consequently, to that extent, yes, the MBA is not bad off, in the sense side lobe remains constant. But imagine that I have a direction of interest. I have to keep monitoring here, but I have monitored some activities happening that I need to have a relook. I cannot take my antenna back and come back because the mechanical inertia. So I go through one cycle of rotation and come back after 4 seconds. By the time my threat has vanished or gone somewhere far away, so many issues are there. Whereas if you are having an electronic antenna which can swiftly shift from one place to the other extreme in no time, there is no time for it to shift from one place to other place. There is no control on how long I can look at it. I can continuously look in only direction. I can keep putting the beam in the same direction. There are many advantages ASA has got. Last but not the least is it can have a survivability under the sort of failures. That is, we call it as a graceful degradation. 10%, 20% we can tolerate. But then when I say 20% or even 10%, it is not that bunch of them right in the center all fails. 10% only, why not accept it? May not. But if you have a really uniformly distributed or a distributed, which is really practical, you will be able to survive. So it is not as critical as MBA. One TWT fails, they have alternate TWT to change on the flight. It takes couple of hours, but still one TWT failure, immediately the mission is stopped. Whereas here the mission will continue even as much as 10% of the system as long as it is distributed in a fashion. So we also started with our own indigenous way of working in terms of slotted array. So we have made in the ATS tower, you can see, probably you may be remembering that ATS, we have put that array which is about 6.5 meters by about 1.2 meters, completely slotted waveguide array. Beautiful pattern we could get, well below 40 dB, and this is what we flew in the Arakonam exercise in this aircraft. That is in 1999 we flew on January 8th. There was an accident, and incidentally I happened to fly the day before that crash, the last but one sortie I flew in that aircraft. So I survived and probably to finish the next one. So if you see in the world, there are a set of them with a conventional, even today they are existing, not that they are not there. On the other side, including Israelis and Ericssons have come out, Saab, today it is called Saab, they have come with another version which is electronically scanned with a ASA type, and fortunately we also went into that category. And as I said, the advantages are whatever I said. Next one, as I told you, the water cooling versus the air cooling. So you have got an air inlet and the air goes down, and what you are seeing as a black one, the 5 pieces are there. They are the power supply. That means I get a 200 volts DC. get all my low power, low voltages there generated, that also in a distributed way. Thereby, they are not, if one failure will not make a difference for all of them. We even thought we'll cross combine so that randomize and all those things. Ultimately, we got restricted on 5 of them distributed in certain fashion. So most of the heat is from the power supply, so it eliminates the heat. After that, the air goes up, air enters like this and goes up through the channels wherein these TR modules are kept. The side of the TR module, the air goes up. While it is going, it will remove the heat. This is entirely a new design when compared to what in those days similar exercise was done by Ericsson's. Ericsson's have also done something similar to this, but they have a sort of a duct in the top and duct in the bottom. If you see here, we have got a rectangular duct and we have got a rectangular duct in the bottom, whereas they have got a tapered duct in the top and tapered duct in the bottom. The tapered duct in the bottom and top is necessary. If you happen to see any a barbecue or whatever it is, you will see that air pipe or the gas pipe comes down and the burners are there in the different distances. Unless otherwise you control the pressure, you will not get the volume of flame coming out of that will be uniform. Likewise, if you don't have the control of those shape, a simple shape, you will not get the power, the air going in all these places in a uniform way. In other words, most of the air will gush to the extreme and cool those TR modules. The beginning TR modules will starve of the air and then will die. So the basic thing is you have a taper and then keep putting more and more pressure, and the collection side also reverse taper is there to do that. But then if you have to remove one TR module anywhere, the entire taper in the top has to be lifted up. You cannot, change or maintenance. You remember that the word what the maintenance was given, they give you in time, within so many minutes I should finish this or whatever it is. We have segmented them into 10 portions. If any TR module fails, because there is no duct at all, that duct is uniform everywhere, we have a way of controlling or taking whichever the TR module wanted. But then how it works when it is not working for a barbecue or somebody else, how it works. For us also, you can see that initially if you don't have any duct, the variation in the air going both positive, excess as well as negative. Whereas what we do is, there is an aperture here through which the air goes. There is a plate, there is a metallic plate is there. The TR modules are identical, we cannot change them. If you change them, then I have to make first TR module is so-and-so, 1/60th TR module is so-and-so, like that you should have. And I have no replacement capability, but I should have them identical. But then the bottom, wherever that goes, the aperture we control, which is one of the tricky issue. So we did, and ultimately we could get that. And these are all the hard spots, well within the limits of expectation. As I was telling you, one other thing is we had a choice to go for a redom design. This is what Ericsson's is doing. You have slotted array, no doubt, but then you have got a sandwich, C-sandwich redom separately, right? Which is at least quarter wave lambda with respect to the surface of the element. You can have them, but then you look at the variation. First of all, this is having first skin, next skin in between your honeycomb. So you have a variation of the losses, first of all, more, and it also varies with the angle when you scan. It's not a constant. Whereas what we did is, we used a very thin film. At this point, this is a slotted array. Right on that slotted array itself, very thin film we have used. Very thin means around 0.6, 0.4 or 0.5 mm, mm. And that thickness rated with some, I told you that ESD is one of the issue. It is coated in such a way that even ESD it will take care. And we use the technology what is used by ISRO in sticking them. We use a proper glue and then gone for a, sucking the, I'm forgetting the word. So we went for autoclave and used it very nicely. But then our misery is that it was stuck very nicely, mechanically wonderful, but electrically it was acting poor, because the slots where there is an aperture in terms of mechanical, extra glue went there and was standing there or get dried there. And those glue are really lossy ones. It is a good in mechanical, but electrically it was not all good. So consequently, we had a big problem in terms of the return loss was poor, the gain was not matching. So we devised certain mechanisms by which the glue at that places will be controlled, and there are a lot of work done on that itself. The next one is what is shown is we have assumed that it is a Faraday's cage is there. So the lightning, it can be probably protected, but we have to prove. Otherwise, the certification people will not accept. So we have done some experiments with electronics inside, working and non-working. We could succeed because it's a totally metallic gauge, and that's an experiment conducted. The next one is sort of very, the accuracy much more reliable, much more accurate than whatever otherwise we would have done. We have to do. The cladded radome is the ultimate this thing. I was talking about icing. So the icing, we need to know where exactly I need to protect. Is it ice is going to form all over? No, we all know in the case of aircrafts also only the control fins and the tips are somewhere it is getting normally ice is formed. We got two choices. One is never allow the ice to form, or ice to form then break it, which is to want to be selected. Never allow the ice to form means we have to continuously waste power and heat up that edge, and thereby ice cannot form. It will just like that melts instantaneously. Whereas the other option is allow it to grow or build up there, but then you have what is called bellow. The bellow is nothing but it cracks it after some time. All that our condition is, again the piece not more than 65 grams cannot go into the engine. As long as that is taken care of, we are okay with that. What is the problem is that we have got a hot spots, including the front nose of the or front aperture of the antenna. So that is what is our responsibility. In addition to that, the chin of the dorsal, we call it. Chin means just below that there's a stagnating place. As long as the velocity of the air is stopped at even an instant of time for a velocity 0, that is the place the ice will start forming. Once it starts forming, you cannot control it. So you have to have a bellow. So far our dome was very convenient. Now we got into a complication and we need to have a sort of a bellow by. This is coming from the bleed air of the aircraft, we can use it. The power consumed is delta or no power consumption at all. Whereas if had I put an electrical heater, that would have melted it, I would have lost 5 kilowatts of power. What is the problem in 5 kilowatts of power? When you are having so much of this thing, we will have an endurance 10 minutes less. That means I will not meet my requirement. So it is a very, very, sort of a debatable. Ultimately, we will end up in this. This is it's a sort of a permanent solution. It is used conventionally in all the aircraft leading edges. So why not this? But we have to make something specifically for us, and ultimately it worked very well. Now the question is, bleed air has to reach there. It's not the question of only leaving it there. The antenna design, whatever we started, you have to stand still and stop, ensure that the bleed air, that tubing is done. The tubing has to be done in such a way that there is a possibility, water always, at the end of every journey or whatever it is, you can see that drips of water coming in. If those water droplets are completely drained out, there is again a possibility of they becoming ice in the next takeoff. So we have to have a mechanism by which a steady slope, you can see that this mechanism by which we have done is, it's a simple way of doing it. A steady slope is, natural slope is given to ensure that water stagnation is avoided. So every aspect of these things will make you to stop your design and look back and do some more changes and come back. This is what I was telling, the bird hit. Bird hit is one of the, whether we like it or not, we need to take care of it. It can happen once in a way. It may not even happen, but still we have to be ready for that. This is how the whole picture comes up. And there again we had a problem of Indian laws with Maneka Gandhi refusing to allow us to use a real chicken for trying out this 4-pound bird. So we have generated some gel and then we equated it and made them to accept, because the certificate agency has to agree. Ultimately we achieved that also. Then the whole thing is to be assembled, because a huge unit going on top of the aircraft. Okay, I'll finish off fast. So the basic thing is we have to, certification issues, so we have to do it quickly. Ultimately we come to the pattern, because we have to, ultimately it has to be an antenna. So we have got two-way side lobe better than 55 to 56 dB supposed to be obtained as per the requirement from the ground clutter mainly. The next issue comes up saying that yes, we have done everything, you have seen everything, how the pattern will be when it is radiating because the temperature can change. So we have to subject the TR modules for various temperatures and study that. The next issue, even you may know, Wedgetail had a problem of the height between the body of the aircraft and the dorsal being not controlled. They have to repeat even after certification was over. So we have done enormous study and ultimately found out the place. Then the last but not the least is we have to have a air-to-air refueling. That's of course one of the new exercises we did. But then the question comes, in case of one not a proper connection wherein this joint, if it is slightly meanders, there is a possibility of fuel coming out, and if that fuel happens to go into your dorsal, what will happen? So those questions are to be answered. Enormous study has been done. Ultimately we satisfied all those things. Then in 2015 February we are lucky enough to bring in PM and explain to him and show him the whole thing, and that time the exhibition, Air India exhibition, Air Show exhibition in Bangalore, this was the only indigenous solution, so he was very happy. He came to us. Then in 2017, we could hand over to Dhanava, he was the chief. And in 2019, I am proud to say that we could use it in the Balakot, and foreigner explained that they could, India could strike with sort of a old or a conventional MiG aircraft, the F-16, only because of the eye of God, that is none other than AWACS or AWNC. Subsequently, we have made 2, then one more, 3. Presently, last week I was in air headquarters, they are asking us to make 6 more if possible. So there's a small team, a dedicated team, done the job, could succeed. That's it. Jai Hind. Any questions? Otherwise, you can ask me later also.
Thank you, Christopher sir. Any questions from audience?
Just a minute.
In what ways this AWACS helped us in Balakot?
Whatever I read from the foreign reporter, not our own, I can share with you. They say that from the MiG aircraft fighting the F-16 or turning it down into the, say, F-16 is not going to be easy. So naturally, before our aircraft can see them, they could have seen us in their radar, right? But the point is, we had an advantage of AWACS at that point of time. They may not have deployed theirs. So they were not switching on their radar. I mean, we were not switching on our radar. And for our fighter, this was an eye. This was at the back. This could see the enemy coming and keep giving a command, go here, do this, do this, do this. So he could easily manage it. That's how the thing has happened.
Yeah, very good talk.
Thank you,
Mr. Christopher. And it shows that what is involved not in design, but also how to a lot of problems, mechanical, manufacturing, other problems, operational problems. Yeah, very informative. That's what engineering is all about. I have 2 questions, if we have time. So first one is you showed one of the antennas where you have something like 79 different antennas, different frequency bands, how you collocate them. So do you use any software to optimize, or what is the software?
Yes. See, first of all, we study with conventional, wherever possible, HFSS. Otherwise, there are so many other software, like equivalent to GTD or a GO only. We use them. And have all those frequencies, which is most critical time, what frequency can be used, we have got another one list. So as far as the user is concerned, he is not knowing what we did. We have pre-done that because the antennas are fixed I have control only on the space. I leave to them the frequency, I leave to them the time when they can operate. I tell them at this point of critical time, if you use this frequency from this antenna, you are likely to get disturbance in this antenna to this extent. Would you like to use or not? So they said, put this in red, put this in yellow, or put this in green. As far as they are concerned, what magic we have done, they do not know, but we have given an advisory. That's the software we did it. And the primary computation is coupling between the two antennas, nothing else, keeping the structure same.
But the actual problem is not at the antenna level, you have to do at system level.
Yeah.
Because some are transmit, some are receive.
Right.
So I think there is software called Savant.
Okay.
Whether you're aware of it.
No.
So we use quite a bit.
I see.
Based on geometrical optics initially,
Okay.
and GTDs involved.
I see.
So what it does is it optimizes at the system level.
Okay.
Either ERP or UOT.
That's right.
So that's where I think we can put a.
I will make you. Right.
Low gain receive.
Okay.
To high gain transfer.
That's right.
So,
Right.
what are the losses, front-end losses with this system?
In the case of TR modules?
No, overall. Yeah. Not just TR modules.
Uh-huh.
From the antenna up to the amplifiers.
Oh, between the see, we have got about from the element to the LNA, the cable is of the order of maximum is 0.5 meter, and so the losses of the order of about 0.2, 0.3 dB. With the connector losses, another 0.2, 0.3 on either side. Within 0.5 dB, we could get it, and the LNA per se is about 1.2 or so for S band. So that's the order of loss we have.
40 dB side lobes is really interesting.
Yeah, that is 40 dB side lobe in the what do you call it, the mechanically managed. Whereas in this it is not 40, it is around 30. I said two-way side lobe. That means transmit, receive. If you add them up together, it went up to 55. That was the requirement. So in the case of finally for detection, you work against the clutter, ground clutter versus you are detecting this one. There the mattering, the clutter from the clutter limited case it becomes. The radar itself is operating the clutter limited case. S by C plus N. So the N is no matter, the C is the mattering. So what C comes from elsewhere matters on the transmit and the receive. So if you don't control much on the transmit side, we try and make it uniform, because then you will unnecessarily land up in inefficiency. Reception, we put a 30 dB or a 32 dB, try to get it. That's what we achieve.
Thank you.
The another one we used to think, but we didn't do, is they say you try and share the side lobes and nulls of your transmitter and receive. Thereby you get your average side lobe comes down, then you get a bane. It happens, but for a certain velocities, still you will see a patch of raising.
Good morning, sir. You have used electronic beam steering. So what is the range of steering? How much range?
In this, we could stretch it up to plus minus 60.
Okay.
User is pushing it to 70. We say pat will be so bad. Extreme case you can do it, but not otherwise. The inter-element spacing is kept in such a way you can happily do it up to 60.
Okay. So, in electronic beam steering, is it possible to steer the beam in azimuth continuous to 360 degree and in elevation from 0 to 90 degrees?
With a planar array, you cannot go more than plus minus 45 or stretch it up to plus minus 60. So if you have got 3 arrays,
okay,
you can have a 120, 120, we can have 360.
Okay.
That's why then you put a radome. You cannot have a planar surface like this. This will have a maximum, we advise up to 240 degrees coverage with this. So a pocket of 60 degrees in the front, pocket of 60 degrees in the back is not covered.
Okay.
So what they do is in the flying, if at all they want to cover, they slightly meander like this and go and take the coverage, if it is essential.
Okay.
But I have come across invariably a sector only, even that plus minus 60 also they never see.
Okay.
They have a very limited, they got a lot of intelligence, they do it in a specific area.
And sir, compared to this mechanically steerable, in mechanically steerable I can get like continuous 360 because that is based on reflector surfaces. So what is the limitation Suppose I think in electronic beam steering, you can steer, but for steering continuously 360, I can't get the performance. But in mechanically, I can get. But which is the best option, suppose for communication, ground-based communication to the satellite?
No, in anywhere you talk about, if you would like to switch from one place to other place, in a mechanical, can you go back? You are rotating, you go in one direction. If I have to come back to you, if it is a 4 RPM or 5 RPM, I take 5-6 seconds to come back to you. If I would like to look at you again and again, can I do that? If I like to stare at you, can I do that? Whereas here, electronics beam, I put it and I can stare indefinitely. Nobody can question me. So it is called energy management. In those aspects, definitely ASA is a better choice. But yes, with respect to the bore side, with respect to the so-called the planarity, if you scan with respect to that, the beam broadening will be there because physical aperture from that direction is effectively less. That's the reason.
Okay. So you use that cladded dome.
Right.
So what are the benefits of because first time I am hearing that cladded dome.
So as I told you that, one is that the loss is less and it is sort of an invariant with the look angle.
Okay. Okay, thank you.
That's what I'm saying. If it is, you try to put a 0.2, 0.3 mm of, it's about a 0.4 maximum. For that thickness, we didn't see any beam, meandering or shifting. Squint you are talking about, we didn't find any squint.
Thermal simulations also you did along with the antenna performance in the radome?
You mean to say performance of the radome would have migrated or changed with the temperature?
Max and minimum temperature, what is the performance of antenna including the radome?
We didn't do like that. The phase shifter separately we put in the chamber and did enormous amount of studies for all the temperatures. Likewise, phase shifter means TR module itself. Amplifier, everything put together as a TR module. The radome material separately we characterized. Both radome character was not changing. As far as the TR module is concerned, it was changing. We have got a lookup table to take care of that.
What's the power added efficiency out of silicon?
No, we have used gallium arsenide in this case. It is around 27% or so.
Plans to going to?
That's what I told you. Last week, of course, I am out of the whole loop, but still last week Air Force called me to just talk to me. During that time, they are requesting me to do that. We will go for hopefully silicon as a chip, followed by the final driver will be nitride, gallium nitride. That's what the plan is.
Front end is gallium nitride.
That's because they would like to have about 140, 130 watts of power each module or each this thing. You will not get from silicon that much at this point, to the best of my knowledge. Our efficiency will be very poor, so we'll end up. Thank you.
Thank you. There has been a fantastic session from Dr. Christopher sir. He has given all the insights and the technicalities involved in the antenna arrays that are mounted on the aircraft. So I thank him once again for giving such a beautiful talk. Let's quickly move on to just a minute before we move on to the second talk. I would like to invite Dr. Ashutosh Kedar sir from LRDE DRDO Bangalore to just give away a momentum to Dr. Christopher sir.
So he'll give momentum.
Very nice.
Thank you.
Thank you, sir.
Thank you, sir.
So we'll quickly move on to the second talk, the keynote. The chairman and co-founder, QuadGen Wireless Solutions and former president and CEO of Lucent India, Dr. C.S. Rao has had a distinguished career in telecommunications. He is the member of HLF for Department of Telecom, Government of India on 5G network rollout policy and helped ASSOCHAM, CII and FICCI for driving telecom policies. He is the government board member of Cloud Computing Innovation Council of India and played a key role in cloud computing policy recommendations at Department of IT, Government of India. He is one among the 5-member team of Smart City Architecture Policy and of Niti Aayog and one of the 3 HLC members of DOT on National Optic Fiber Network, NOFN, recognized for National Telecom Network Securities Certification Framework to DOT. He conceptualized and launched $3 billion telecom network infra in India under his leadership. Also helped broadband wireless access spectrum auction in 2010 for $2 billion. He has started the world famous Bell Labs in India in 2004, first ever outside of USA, and pioneered the concept of 21st century network for British Telecom in India. In addition to holding executive positions with BT India, Intel, Tel Labs, CDOT and Reliance Communications India, he is also the former president of AUSPI India and current chairman of WiMAX Forum India. Dr. C.S. Rao has been honored with Bell Lab Scientist USA Business Leadership Award, ASSOCHAM, a National Chamber of Commerce, and Innovation Leadership Awards, Tel Labs USA. He has received National Research and Development Council Award from Honorable President of India and Telecom Person of India 2012 Award of the Indian telecom industry. Now, I would like to invite our next keynote speaker for the day, that is Dr. C.S. Rao, Chairman and Co-founder Quadgen Wireless Solutions, to deliver his talk. Sir, please.
Am I audible? Audible? Okay, thank you. Digital transformation in wireless communication network architectures and the role of AI/ML is the topic on which I am going to talk. And as you can see from here, the densification of cell sites is very high, inter-site distance and monopole mounted BTSS is the order of the day, and not the huge towers that you see, which is a lattice structure towers that you used to see. The scale and unique transformational attributes are round the corner, and in the USA, Korea and Japan, the densities of cell sites at over 30 plus per square kilometer has become a reality due to the 3.5 gigahertz to 4 gigahertz spectrum, and also the millimeter wave when it happens, and the cell sites are becoming very, very high. So, as the picture depicts, the Y gig area is all around, the coexistence of all the technologies and carrier aggregation across all the technologies, so that you have the high bandwidth of the RF channel, and when once you have high bandwidth of the RF channel, you get very high air interface throughput speeds, and that is the biggest transformation that is taking place right now in the wireless area. The next, sorry, I think, yeah. It's all around, the 5G is all about the convergence of IT, telecom, media and internet, including the silicon and application. 5G is just not a wireless interface or a wireless technology. The technology world is at a stage where a wide array of technology domains are all impacting the fabric of human entity. As you can see here, you have AI ML algorithms, you have deep learning algorithms, you have smart network architectures, you have lots of analytics that takes place of the radio network parameters. AI based algorithms are required for ensuring a best quality of experience or quality of service. So, the effectively what is happening is a bio, information and nano, bio, info and nano are collaborating to create and provide a user with unique customized digital apps. Today the network architectures are transforming themselves into what is known as no more a infrastructure as a service or a platform as a service or a software as a service. It becomes X as a service, network as a service is one among them. So, the digital transformation, you must have heard of this word this terminology so many times. So, what is digital? Digital is all about what is about a fast paced change, a very fast paced change with the rapid adoption of the state of the art technologies. That is why this is called digital. You call it as a digital infra, you call it as a digital future, you call it as digital lifestyle. Anything and everywhere people use about digital economy, digital payments, as you can see what is happening around the mobile apps for payment. So, digital is all about the fast paced change, and transformation is all about innovation and the evolution and the scale at which the network is getting transformed. So, it is all about the reinventing the tools for automation and reinventing the engineering services, so that the innovation takes place in the telecom operators, where they have now 300 million subscribers. If 300 million subscribers have to be served every day for their different applications which are unimaginable, the scale and the scope of work involves hell of a lot of digitized operational model, and it requires a lot of agility in response. It requires lots of analytics based decision making, and it also involves hell of an automation centric operations. And these 3A based service assurance focus is the one which leads to the adoption of AI and ML and cloud as an operational requirement going forward into the telecom operations. So, with the result, so the 5 technology pillars that is impacting the digital decade of wireless networks are these 5. As I mentioned, 5G, LTE and Wi-Fi 6. It's okay, right? This is not working? No. I can move about, right? Yeah, thank you. Then in addition to that, the softwareization, virtualization and automation are driving. What you used to see as a router as a physical element is no more a router. It is just a protocol software running on any standard computer servers, and a bunch of similar, same is the case of a Wi-Fi controller is no more a physical element. So, everything is around a software defined networking, and network function virtualization is taking place, and what we used to see as a RAN, which used to be known as a single BTS, now is giving way with its proprietary protocols between the BTS and the core network, is now giving way to ORAN and also virtual RAN, and going forward already it is a reality, it is a cloud RAN. So, what you have in the radio network is just nothing but the antenna, adaptive antenna unit. I think, and that's RRH, remote radio head, is what all you will have at the cell sites. So that is another way in which the RAN is getting transformed. And going forward, another major technology that will have is our 60 gigahertz and also the artificial intelligence. And artificial intelligence is all about analyzing the real-time complexity, as I mentioned, and all the computational needs that you need to do in radio resource allocation and monitoring the radio resources and ensuring as the call is migrating from one cell site to another cell site, when so much of densification is involved, you need to monitor so many neighbor cell sites. So automatic neighbor relation management, apart from a single radio cell site radio resource monitoring, becomes much more important. In addition to that, the interference management also becomes important because the cell sites are so many in density in number. So that's where the power of AI/ML comes into the picture. So with that, as I mentioned, the digital transformation is taking place in all the 4 layers, and alongside a 5th dimension exists, which is also the business service transformation and customer experience expectation. So there is the RAN transformation, there is a transmission network connecting the RAN to the core. There is the core network itself is getting digitized and softwareized, and so the skills required are going to be in all these 4 areas. All of you as youngsters and all of us as engineers and all the faculty members have to get ourselves transformed to acquire new skills and adapt ourselves to the going forward area. So the telecom networks are into transformation area. Telecom networks are truly becoming, reinventing the telecom service provider into a cloud provider models. A telecom network provider is a search service provider today, an information service provider, a digital storage provider for you, a content application service provider. So they all run a software development application, the SDP, software development platform, on which the application delivery platform is also created, every operator, and then delivering that through the network that they have of the core network, or the digital private network services also an operator can provide for police separate network, for military separate network, for enterprises, for banks. So the digital private network service provider also is happening apart from what they are doing it for business to consumer, that what they are providing to each one of you as an individual service. Now they have to provide a network wide service also. So anyway, the bottom layer is always about access network of 4G or a transport network or a 5G access network or fiber to the home or fiber to the building. So the underlying principle is IP, mobile, optics are the 3 simple technology domains which are today giving you a hyper connectivity in the today's connected world. The computers in communication and cloud architectures in communication is another huge transformation. Sorry, I am pressing too fast. So the digital transformation in a telco, as I mentioned, is all around. The services are getting varied. It is all mobile everything today. M-Pay, M-Learn, M-Health, M-Banking. So everything is around that, and that requires a super fast, automated, zero-touch network element configurations across the elements, right from the RAN to the transmission to all the way to the application provider, and that is what is a very important aspect of the transformation that is taking place. So a digital telco in that sense has to embrace the latest next generation operational services capabilities, OSS capabilities are very much essential. a unique digital operator architecture around cloud, SDN, NFV models is the path on which all the massive networks of high capacity, for example, a Reliance Jio today is having 320,000 BTSs connected around 1.2 million route kilometers of optical fiber and having something equivalent of about 100 petabytes of storage in their network. So, that is the kind of transformation taking place in a telco operations, which is an order of magnitude, just for your information. So, the evolution of mobile broadband, if you see the scale, service and infrastructure scale from 4G to 5G era, mobile broadband is going to be EMBB. So, that is what it is likely to be. So, the order of scale of magnitude is going from 100x to 1000x. So, that is the transformation that is taking place. A machine type communications, which is now the order of the day, like as Dr. Christopher was mentioning, how many types of sensors they have on a vehicle, on an airborne vehicle, and same is the case for any walks of life that we see around, even wearables. So, we have lots of sensors and all these sensors have to be connected. So, the machine type communication, if you look at our own house, we will be having at least 6 to 8 types of devices which are all connected on the Wi-Fi around a 5G mobile handset or a 4G mobile handset. So, the machine type communication is having a phenomenal increase in scale. Similarly, the reliability, as Dr. Christopher has mentioned, reliability and latency requirements are phenomenal required, especially when it is the airborne communication, UAV communications or connected vehicle C-V2X applications around 5G. And the devices used in the base station are now no more CPUs, they have to be graphical processor units. The memories that are used in each of these base stations are far higher of about 10x memory that is being used. Fortunately, the memory cost per bit has come down and the power consumption has also come down, and hence each of the BTSs is now almost like a supercomputer. And so, that is where the order of erstwhile supercomputer era is coming to. Every point of presence is having that kind of order of magnitude. The quality of service is increased, has migrated to quality of experience. Every user wants to have an experience. If I want to have Facebook or WhatsApp, I would like to have some degree of quality of experience associated with it. And also I demand certain kind of service level agreement when I am using a video on the YouTube. So, this is where the whole world is changing in terms of evolution of mobile broadband and the service and the infrastructure scale, and element management system and network management system has to now be capable of interacting or interrogating each and every network element. 300 million devices is one order of magnitude as the subscribers, but 300,000 BTSs, points of presence, are another magnitude of elements which have to be constantly monitored from a centralized element management system or a network management system. And so many more transmission nodes have to come. So, this is the order of scale that is happening, and on the network management side it is all the more complicated because now it is all around analytics and service enablement, etc. So, the bottom line is the scale and scope of work is changing, and hence the AML role becomes extremely important. Oh, sorry. And you can see the user equipment is the digital transformation, the user equipment, the sensors and app driven multiple services are there in the embedded things, and both in the consumer and enterprise side. just with one handset and different applications, you are able to invoke so many services, be it an IoT service or a transportation for autonomous vehicle or a tactile internet or a smart grid application, AR, VR application, what have you. We have implemented one in smart city in Bhubaneswar in this state of Orissa, where from the app people are able to have smart parking, smart surveillance, smart G2C application platform, and the sensors are put on as high as 52 watts to create the embedded sensors on the floor for parking, so that they are able to see how many vehicles are parked, be it a two-wheeler, four-wheeler, not only the infrared sensors, but also the sensors embedded on the ground. So that a centralized monitoring system of how many parking slots are available at any place, and such an information can be broadcast as a person is driving down from Bhubaneswar airport into the city. There are 6 or 7 major parking slots are available, and people get information, hey, you can go to this parking lot where you can park your four-wheeler or two-wheeler. So that is the kind of application that are coming up. That is the digital transformation taking place, and you can see all that from your own handset. So the radio network, is getting transformed. As I mentioned, RF channels with what used to be a 10 megahertz is now becoming a 400 megahertz or even 2 gigahertz RF channel. The spectrum required per telco, what used to be a small spectrum, now they require a minimum of 300 megahertz to 1 gigahertz of spectrum. So that is the amount of spectrum. What used to be a modulation order of 64 QAM that you all have studied as students, or all the faculty members have seen. Now today on the access side already the 1024 QAM order has happened, and on the microwave side it has become 4096. So that is the order of QAM modulation that has taken place, and that is another huge transformation. Antenna orders are changing from what used to be a 2 by 2 has become a 256 by 256 MIMO. And what used to be an integrated BTS will become a decomposed BTS with remote radio head, a baseband unit controlling X number of remote radio heads in X by Y square kilometer, and the RAN itself, entire radio resource management is going to the cloud. So that way it becoming a virtual RAN is going to CRAN also. So that is the amount of transformation taking place in the RAN. So to pictorially see this, this is where what used to be the antenna earlier is now becoming a adaptive antenna array or active antenna system as a part of the remote radio head, sending beams to each and every radio user equipment. So this is the kind of transformation from passive to active and sectors to 3D beams on the MIMO and array. I think this is the transformation that is taking place in the antenna technology. Sorry. And the intersite distance, as you can see here, typical cell site coverage, dimensioning and prediction. So this becomes very important, and 3.5 gigahertz N78 band of 5G is being shown here. So the intersite distance is hardly 2.6 kilometers. In fact, it may be much lower. So when once you have this kind of an intersite distance, and this is the order of beam forming, so you can see the interference management techniques that has to be used, and that is where the need for using the network performance monitoring on the optimization efforts have to be done to do the interference mitigation, the neighbor relation managements, and load balancing of the radio resources has to happen, and this is how the entire channel prediction and channel quality monitoring takes place. And this picture indicates what is the complexity that is going to be involved when you move from 4G to 5G as the cell densification takes place. Sorry, I keep pressing very fast, I think. Yeah. So, this indicates to you, even in a neighborhood, what is the residential neighborhood, you use no more the big antennas that you see today on the big towers. For all you know, it may be your electric pole on which you put a small adaptive antenna array, remote RRH, only having the adaptive antenna array element, and that is covering with 3D beam forming, so that the users in their homes will have the beam tracking, beam acquisition and beam latching, and hence they are assured of the throughputs. And the throughputs that are being seen and experienced today in the United States in 5G era is almost reaching 600 Mbps on the air interface in a 1 by 1 square kilometer grid, serving so many neighboring homes with 600 Mbps of downlink and 200 Mbps of uplink from a fixed wireless terminal or also on the mobiles which are around that neighboring cluster of neighboring homes. So, that is the order of magnitude that people are seeing it today. So, what used to be a big integrated BTS is now becoming, in the second part you can see there, it is not just the integrated BTS, it is only a BBU, but the radio heads have gone on top of the passive antenna, and the RRHs have moved to the antenna at the roof, at the tower top. And as you go further, the transformation is taking place where the only active antenna with the radio unit is there on the top of a small pole, and whereas the antenna, the CPRI cables are all taken and connected to the BBU on the optical backhaul network. This is another transformation that is taking place around the RAN and antenna that you can see. So, this leads to an architecture where you can see what used to be a single dedicated on the bottommost one, where you have an RU, radio unit, data unit and control unit. It is getting further split into radio unit and data unit, then it is going to radio unit only, and that is how, and all of them, all the front haul, back haul and mid haul, the transmission network is also getting changed into 3 layers: front haul, mid haul and back haul. So, this is another transformation that is taking place in the case of the RAN network. So, this summarizes the digital transformation that is taking place in the networking area on the RAN side as well as this. So, a distributed RAN or a dedicated RAN is going to a virtual RAN is becoming a CRAN, and CRAN now is also a part of the ORAN, Open RAN, where radio network BTS can communicate with any core network. Earlier it used to be if an Ericsson BTS is there, it can communicate only to Ericsson core network and vice versa. So, all this will not be there going forward. The transmission network itself is also going through a lot of transformation. The transmission network, what earlier we used to have in the 3G is 155 Mbps to 1 gigabit, now 1 gigabit to 10 gigabit. So, you can see where the optical fiber speeds are increasing. What used to be a 1 haul is becoming 3 haul, as I mentioned, and what used to be an intelligent transport IP transformation, now it is becoming an optical SDH is becoming an IP intelligently routed optical transport network, and speeds of the transmission layers are increasing from 1 gigabit to 40 gigabit to 400 gigabit to 16 terabytes, and 1 terabyte wavelength is happening on the optical fiber. So, that is the amount of transformation that is taking place. The core network, what used to be a bunch of routers, a bunch of gateway elements, a bunch of network elements, is all becoming extensively softwareized. So it's all becoming virtualized. Now the 5G network, 5G core network is nothing but a set of virtual functions, whole lot of them, right from signaling to the control plane, to the bearer plane, user functions, user plane functions are all nothing but a software virtual network functions hosted on a server form at the core network. So that's what is the order of the day, and that's the transformation that is taking place in the core network. So the core network, if you see the transformation of the core network, the core networks are no more a hardware, it is moving from hardware to software. It is no more integrated. Even the core network is not going to be put up at one per the state model. For all you know, it may come at one per every district you may have. So that's what is known as multi-edge computing, and the core network, what used to be there, now will be coming at every town for all you know, and that is where the networks are getting transformed, is even the core network. The physical is becoming virtual, a geolocation is becoming a cloud centric. So Amazon and Microsoft are advising the telcos, hey, you don't build any core network. We host the entire core network operations on our cloud Azure. How many subscribers you want? You want 300 million subscribers for Geo? We will host it on our cloud. You don't have to do anything on your place anymore. So you only build the fiber network, you only build the RAN network, and the core network will host it on our public cloud. And that is the kind of proposal that they are making all over the world. Amazon is doing it, Microsoft is doing it, and that's become a reality, and the trials are going on, and that is another big transformation that is taking place in the core network area. So in summary, the 5G end-to-end network architecture is going through a transformation path. As you can see from here, the RU, remote radio head, RU-DU going through front haul, back haul, and also going through a bunch of virtual network functions being hosted. So this leads to the consumer packs. Now the spectrum, site throughput, area throughputs, and number of subscribers and core network capacities are significantly transforming. As I mentioned, each core network is now likely to have about 2 petabytes of total RAM capacity on the core network. On the air interface, on the site throughput of 4 gigabytes in LTE going to 6 gigabits in 5G, and 120 Gbps throughput on 5G NR millimeter wave radio. So the area throughput per square kilometers are now going from what used to be 15 gigabits, now it's becoming 2 terabytes in a 5G NR microwave, around 1 by 1 or half by half square kilometers today. Earlier, the subscribers that you used to serve used to be on a per square kilometer 25K subscribers. Today, if you look at Bombay, Nariman Point, you have to serve 1.4 million subscribers. LA downtown, Los Angeles, is about 1.8 million subscribers they have to do in what is known as a golden square mile area. So that indicates to you how much of cell sites are required, how many rooftops are required for antennas, and what is the order of magnitude of the subscribers that you need to serve and the area throughputs that you require. So that is the order of transformation. So all this leads to the next phase of my talk, which I will conclude in the next 5 minutes, I hope I am not taking more time, is the path of why all this leads to, all this leads to a telco data pipeline. A telco data pipeline from multiple data sources has to come, and this leads to the era of the real AI and ML era. So you will have the data coming from network elements, you have data coming from the OSS platform, you have data coming from social networks, You have data coming from any major events that are taking place, if it is a sporting event like an IPL from a stadium. All these types of multiple data sources have to be extracted, they have to be collected, they have to be cleaned, they have to be correlated, they have to be trained, and a model has to evolve, and such models are coming from multiple tracks of data pipes, and so you have to do multiple layers of this data pipeline from multiple data sources, and finally another model will get evolved. So, all this results in a huge requirement of the data science, which is very much essential, and that is the part of the AAML component that I wanted to talk to you about. So, what used to be a model where we used to do the network performance monitoring and decision making from calculation, but now it is no more a fixed formula of 10 by 10 matrix of parameter monitoring, KPI monitoring, and take some decisions monitoring the thresholds and initiate some action to do the network performance improvement. Now you have to do a lot of deep analytics. So, that is the transformation that is taking place, a rule based to AI enabled self optimizing network evolution is coming up. A limited to scalable operation. Now you will have, as I mentioned, the order of network elements that you have, number of subscribers that you are serving in a given golden square mile area. So, a predefined to a dedicated deduced inference is required. It is no more a rule based, a single data source to multiple data source, a static model to a self learning model, and a fixed model to a learned automation, and that learning process is continuously evolving, and that is where a self learning algorithmic evolution requirements are coming up. So, that is where the telecom world is coming to the computing world of AML algorithm requirement, and that is where a multi-dimensional self-optimizing network requirement is very much required, and that is required for self-configuration of elements. And if you have got 300,000 elements, divide by 220 working days, and you can see how many cell sites you have to activate every day and configure them. So, how much of human effort is involved by sending the crew to the cell site, putting it up, configuring it, parenting that E node B or a G node B to the core network, so that that comes into the network and ready for active launch of the service. So, now you cannot have and you cannot afford to have that much of time. People want services faster, people early bird catches the worm. So, if you as an operator is not agile enough to activate the network element to capture that 1 million subscribers, he loses the revenue for that 1 million subscribers. So, that network element that once you put it should have the ability to self configure and self home itself to the core network, so that it is ready with self integration capability and the network gets cuts over. So, that is the self provisioning aspect of the self optimizing networks that is coming into the picture, and then automatically the service assurance has to take place. As the service is moving from 2G to 3G to 4G to 5G, as the G goes up, the speeds are going up, the expectations are high, and if your expectations are not met, we as consumers feel that we are cheated, and so we expect a service assurance. So, for that again the operator has to evolve a model where a service assurance model comes up as a part of his network loading parameters, and network capacity modeling has to take place, and continuously the operator has to see this, and that is where again the self optimizing network models are evolving, and that results in dynamic resource allocation across RAN, transmission and core network. So, that is where the AML role comes into the picture. So, all this leads to one thing, that is ultimately it is the people, it is the process, it is the platform and its partners, and all the people have to transform, and they have to go to learn the robotic process automation tools, AI ML led tools, the engineers have to know the aspects of predictive network healing, robotic process automation, advanced monitoring, analytics, process optimization. So I think this is where the communication world is for a huge transformation era, and that is what offers to you offers to you a track of automated tools for over-the-air testing and integration. I think that's one domain where it's a lot of learning opportunity for faculty and students and industry people. Next gen propagation model centric RF network design and optimization is another area. A transmission network of photonics is another era. IP terabit core network design and coverage and capacity modeling is another era. AML led SDN NFE model is another area. So these are the tracks on which you will be associated with as you go forward. So that summarizes my talk to say digital transformation has set in, is scaling up excessively, and that requires excessive use of the computational power, which means we need AI and ML and data sciences and algorithmic development, not just data science and data cleaning, but we need strengths in algorithmic development, and that is what helps us to take certain network improvement correction actions. So we are set for a great futuristic era of learning and growing with the industry. Thank you very much. Any questions?
Thank you, sir.
Go ahead.
Sir, you were talking about the resource management, dynamic resource management. Now, the thing is that if we are going for centralized resource management schemes, then how it will be benefited for mobile age users when there is a very high demand for quality of service at those ages. And if we are going by theoretical implementation, it will be completely different from the practical aspect, those on which the telcos are working. So I was just asking that whether we should go for a centralized management system or any other management type of services.
No, as I mentioned, am I audible? No. I think maybe I am not getting the feedback. Yeah, I think it's a good question. As the number of nodes are increasing and the number of subscribers per node are also increasing, the radio resource management around a point of presence is one angle. You are asking, if I take a cluster of 10 nodes, all these 10 nodes around a cluster, let us say around Rourkela, around this campus, what is the total number of radio resource management I have to do? Should it be done locally or should it be done centrally is the issue. As I mentioned, the computational power of radio resource allocation and management is getting complex. It is very nice to have a centralized control, which is very easy for engineers to do, but it also leads to certain problems of latency, quality of experience requirements which are being sought by the consumers. So there is a compulsive need from a centralized control to a distributed control, and hence the architectures on 3GPP has evolved models driven first by IEEE and then 3GPP adopted, saying that multi-edge computing has to come in. So the core network, what used to be a huge server farm, is becoming multiple server farms. For example, in what we have done in Bhubaneswar, there are 52 wards. In each ward we have put a multi-edge computing platform connected to a centralized core, where we have put a data center of 15 petabytes of storage. I hope that is the correct order, Arpita, 15 petabytes of storage, and we put about 200 server farms, but the multi-edge computing platforms are also there, of each of them having 100G or 40G each of these 42 watts. Reliance Jio is partnered with Google, and they are putting every 5 watts a multi-edge computing platform they are building. That is why Google has put in $6 billion of funding. It helps both Jio, Ambani as well as Google. So, that is the order of the transition that is taking place. You definitely cannot afford to have centralized control. You have to have multi-edge computing based resource management allocation for QoE, sheerly driven by the type of application that you consume, the type of quality of experience that you are asking for.
Sir, thank you, sir. And that means there will be cloud servers and also edge servers. Those will be sharing their loads and giving the access as per the QoS requirements like low latency or reliability. So, if we will think about AI ML models, so if this type of distributions will come, so definitely whether federated learning models will work for that, or we have to separate different models for the data centers and different models for the edge computing.
I think the edge computing is having both federated learning models also are being used for IoT applications. Especially we did one project where for Oman, where we tried to design the network architecture. I was mentioning to Dr. Sudhakar the other day, they wanted 10,000 oil fields. Each oil field is having 1 by 1 square kilometer. They have lots of sensors at the time of rig. So, all these sensors have to be connected, all these sensors, and oil comes to the rig, to the reservoir, to the refinery. So, at each layer they have sensors, and all the sensor data has to come again, and this is a highly latency intensive application, right. Latency has to be very low, of the order of 5 milliseconds to 2 milliseconds. So, when you have that kind of a thing, multiple models work. So, the algorithmic development that is chosen in the network, in the SON, chooses what is the algorithmic learning model that I need to adapt. They will have all the 3 types of learning models: supervised learning, unsupervised learning, and federated learning. Now, all these 3 models of algorithms are already available as an algorithmic base, and they invoke as a part of the SON which algorithmic model that I need to take, and that is what they activate. Okay?
Thank you so much.
Thank you.
Hello, sir.
Yeah.
I just have a small question. Like I was just curious to know what are the technical specifications of the newly emerging 6G in terms of the data transmission rate and as well as the bandwidth, and how is it better than the 5G?
I think I started from 1G, but I am talking about 5G now. I am a 1G era guy basically, right. I am 65, my age. So, I started when I come up to 5G. So, I leave that to 6G where it is, 5G we are experiencing, and 6G when it happens, what is the carrier frequency that we will be using.
Yeah,
as I mentioned already in my talk, 60 gigahertz is what millimeter wave communication. As 6G comes up, it is talking about 100G to 1 terahertz of the spectrum. So, when once you have the spectrum in that range, the channel width, what I talked about 2 gig channel, may become 20 gig channel. When once it becomes a 20 gig channel, the modulation, the beam forming, and all that spatial diversity of the antenna array gains that you look at it, the per site throughput, what I mentioned around n times 2 gig may become n times 1 terabyte also. So, that is where it likely to go, and that is the area which offers for people like you who belong in that era of 6G, and I am a 1G guy. I hope I will not see it as a realistic experience in my lifetime. It will take at least 10 to 15 years to come. As I mentioned, every technology takes 1 decade. We are just starting 5G, both in America as well as in India, maybe, as we are going into the 5G auctions this time. So 6G is definitely a promising area. Again, as I said, IEEE is doing a lot of work. Whatever IEEE does, later on adopted by 3GPP for standardization. And so the OEMs have to come, silicon has to come, systems have to come, software has to come, only then it becomes a reality. So have some patience. I don't know what you will do with a 1 terabyte package of month that will be given to you by Jio per month. I don't know, I can't imagine what I will do with it. But already 1 terabyte per month package is offered by the telcos in America. I believe they are launching it just this coming week. Verizon is launching 1 terabyte per package per subscriber. So I hope I answered your question.
Thank you, sir. And I had one more generic question. Is the research in this wireless communication saturating towards the AI and ML, or is there any scope of research in the field of core RF and photonics in this area?
No, that's why I think it's a very good question. I think as Dr. Sudhakar was asking earlier a question to Dr. Christopher, I think the coexistence or maybe the boundaries between communications to computing today are more or less narrowed a lot. A BTS, as I mentioned in my talk also, is just not an RF and antenna and a backhaul or radio resource management. The amount of baseband processing that you have to do in a BTS is requiring a multi-core processors, not just CPU, of the GPU capability. And the RAM capability into the BTS is far, far higher than what I have seen around a 2G or a 3G base station. So the convergence of computing power into the communication platform, and that communication platform again driving the MIMO processing and a beamforming processing for directing the beams to be latched on by the user element. There is a lot of AI ML that is being involved even in that process of a link to be established between an end user and a base station. So it is very difficult to say it is being saturated is not the right word. They are coexisting, and that's how the networks will evolve. Okay?
Thank you, sir.
My question in general, as you mentioned initially, number of base stations for a unit area is increasing. So, is there any human hazardous for that?
Yeah, I think I know the two people sitting next to you will be the better persons to answer. Ask them to find out. So.
US and all, I heard there they are pumping very low power in the public area, and they will pump more power in the outside of the city. So, but in our country, like high population density, so is it feasible?
No, I think it's a good question. It's a good concern that you have. You know, our country and China are the countries where we have the highest subscriber density per square kilometer.
Yes.
At the same time, we also have highest concrete density per square kilometer.
Yes.
Unlike America, which doesn't have concrete density, it has a lot of wood. Most of the homes are wooden all around them. I'm sure even Dr. Sudhakar's house may be wooden all around. So fortunately, we have concrete density higher, and subscriber density is higher, and also we have vegetation density higher per square kilometer. So I am not saying that these are the ones which will help you to reduce the cumulative radiation coming out of 1 by 1 square kilometer when you have 30 base stations. Each of the base stations are not transmitting the power at let us say 4 watts or 8 watts that you see today in 4G era. they may be transmitting the power not more than 36 dBm or 30 dBm, 1 watt. And lots of studies have been done. The radiation that is coming out is well below the limits of ionizing radiation. So, one need not be concerned that, need not be worried about Juhi Chawla's campaign after her prime heroine era is over. Now, she became a champion to say, oh, I am against radiation. She like he talked about Maneka Gandhi when that chicken had to be given for that for that aircraft bird hit simulation. So, I take the reference to Juhi Chawla. So, she is raising lot of this awareness, saying that look, this radiation is going to cause cancer or harmful and all this. So, lots of studies have been done. Be rest assured they are false and they are well within the limits.
Mic is off. And one more question we are getting from Nasser, Dr. Nasser.
Dr. Nasser is asking a question.
Okay. Dr. Nasser, I believe you have a question.
Sir, please unmute yourself.
Okay. Sorry.
Thank you very much, sir, for this wonderful talk on digital transformation, where wireless communication plays a key role. Dr. Nasser, I would like to take your question right now. You can unmute and ask. Okay. Thank you, sir. So I would like to call Dr. Sudhakar Rao, sir, to present the floor. Okay, to you.
I am truly honored to get this from my friend and senior.
Thank you.
Thank you very much, sir. Now we will hand over the session to Ms. Manmita to continue with our next keynote talk. Manmita, you can go ahead.
Hello everyone and good afternoon. I'm an undergrad at NIT and I take using art gallery. I'm a senior engineer at the National Propulsion, California. So without further ado, all welcome Dr. And we're elated today, sir. Dr. Chahat, engineer from Rennes, France, the master's in telecommunications, doctorate in signal processing and telecommunication from the Institute of Electronics and Communication of Rennes, IETR, University of Rennes. And since 2015, has been a dedicated microwave engineer with NASA's JPL. Dr. Chahat authored and co-authored more than 100 articles, conference papers, holding several patents. CubeSat antenna designs, written by Dr. Chahat, describes all of his innovative work on CubeSat antennas developed at JPL. He is a co-inventor of the iconic deployable reflector used on the Mars Q1 micro mission, world's first interplanetary CubeSat. The award-winning GainCube mesh reflector antenna used on the first CubeSat, invented by Dr. Chahat. And not just that, he also invented the lander antenna, enabling direct communication from the surface of Europa. It was capable of surviving the environmental conditions of icy Jupiter, despite being 60 kilometers away from planet Earth. Dr. Chahat is the recipient of the 2011 CST University Publication Award, 2011 Best Paper Award from the Bioelectromagnetic Society, and the IEEE Antenna and Propagation Society Doctoral Research Award. He was awarded by Foundation of Rennes 1, Best PhD of University of Rennes. In 2013, he received the Best PhD Thesis in France in Electrical Engineering, awarded by Club EEA. In 2013, he was awarded the Airbus Group's Foundation's Best Thesis Prize in France. In 2015, he received a French Early Career Award for researchers for his notable scientific contribution in his early career. In 2017, he received the IEEE AS Transactions Prize Paper Award, and in the same year, he also received the prestigious Lou Allen Award for Excellence, awarded by NASA's JPL. In 2018, he was awarded the Future Technology Leader Award by the Engineers Council and the NASA Early Career Achievement Medal Award. In 2020, he received the IEEE Outstanding Engineer of the Year from IEEE Region 6. And in 2022, he received the IETE Dr. Sudhakar Rao Award, and he became a Fellow of IEEE. You are truly an inspiration for all of us, sir. And once again, a very warm welcome to you, Dr. Chahat. And without further ado, over to you, sir.
First of all, thank you for the very nice introduction, and thank you for the organizer for inviting me. It is my deep pleasure to be here. Everyone knows how invested I am in India and how much I love this country, and how much I like to visit, and I've been doing that almost every year for the past 6 years, except during the COVID years. Unfortunately, this time I was not able to attend in person, but at least we're able to do that virtually. So I hope I will be able to see you all in person next time. So I'm going to give you an overview of all the work that I've been doing with some of my colleagues at the Jet Propulsion Laboratory on antennas for Earth science and interplanetary missions. And you will see that through all of the missions we are working on, we're able to touch a wide range of antennas, and that truly the work that we do at JPL and for NASA really give us this opportunity to touch at this wide range of technologies for a different environment, and I'll try to show that through different examples of flight missions. The first one I'm really excited to share about is the Europa lander, which is a mission that the scientists are extremely excited about. It's unfortunately not yet on the way, but it's a mission concept that get a lot of excitement in the scientist community, because this is one of the places on the solar system where we think that the likelihood of finding life is the highest, Europa, which is a moon of Jupiter. So one of the main challenges that came up during this mission formulation is the cost of the mission. So initially, the team that put together this mission concepts and proposal had baseline a mission where we had an orbiter that would provide telecommunication relay, and the lander that would land on the surface of the moon and carry out in situ measurements. However, very quickly we realized that the cost of the mission was prohibitive for NASA to move forward. It was more than $4 billion, and for that reason, the review board told us you have to go back and find a way to reduce the cost by half, otherwise this will never happen. And this is what we did. So at this time, the team thought that it was impossible to do what we call direct-to-Earth communication, so without relying on a relay orbiter, because we didn't have any antenna technology that could provide very, very high efficiency. So the requirement is more than 80% efficiency, and yet survive the very harsh environment of Europa, where we have cryogenic temperature. and where we also have extremely high radiation levels. And for those reasons, we had to come up with an antenna design that provides circular polarization at two different frequencies for uplink and downlink at X-band, while surviving this very harsh environment. And this is what we come up with. So this all-metal antenna, which is a large array, which allows us to maintain very, very high efficiency across this very large surface, which is almost, I think, about 85 centimeter by 85 centimeter. So you can see that the main innovation here is this element. So this element, which is entirely made of metal, it's made of aluminum. Here you can see it's a very, very pretty color because it's gold-plated. It's fed by a single point on the bottom corner of this element right here, and allows us to cover these two frequency bands, which is, if you cover the entire band, it's very, very large bandwidth, and provide circular polarization with a very good axial ratio. So this was the main innovation here. So obviously, there has been work in the past where everyone knows that it's possible to make linearly polarized patch entirely in metal. And the trick to do that is to put a metal post in the center because the current is close to zero. Here, that's not the case. So you can see that the metal post is located around here on the element. It's not in the center, and we actually use that to help us generate the circular polarization, because otherwise a half E-shaped element like this would not generate circular polarization, but instead a linear polarization. So that's really the trick here that we use to actually generate circular polarization out of a metal-only element like that. So we first developed this subarray, which is an 8x8 element, all fed with a power divider with air strip line. We actually verified that all of the performance were met. So as you can see here, the reflection coefficients, and here is the radiation pattern, and most importantly, the aperture efficiency, which is higher than 80%. So all of the losses that we get, they are only insertion loss, either on the power divider or on the metal element itself, which is ohmic loss for the most part. And as you can see, the accuracy between calculation and measurement is close to perfect. You will rarely see such a good agreement between prediction and measurements. So just to give you an idea of the achievement here, so we're comparing the performance of this antenna with previously developed antennas. So the first one is the radial line slot array, which across these two frequency bands, so 7.19 to 8.45 gigahertz, they did not achieve more than 40% efficiency. And for I'm hearing noise on the background. I don't know if okay, I'll continue. So on MSL, you can see that the efficiency was lower than 50% efficiency, and MER, which was spirit and opportunity, it was also lower than 50% efficiency. And that's the reason why people thought it would be impossible to actually achieve such high efficiency. So as a result, we got a smaller antenna, a lighter antenna, and as a result, we would get better beam width, 3 dB beam width as well, so much broader, which also allows us to relax the pointing requirement. So then we fabricated a 16 by 16 patch array, and we tested this array across a very large temperature range from minus 170 C to plus 110 C. And we satisfied all of the requirements. And as you can see here on the back, we have a waveguide power divider which divides the power in 4, so we can excite these each of the subarrays. So each of the 8x8 subarray are fed with a waveguide.
Yes,
so this is the lender. At least this is an artist concept of the lender, and you can see where the antenna is located. So before landing, the antenna is folded on top of the surface of the lender, and that's why the antenna needed to be completely flat. That's why we couldn't use any.
Sir, can you hear me? Actually, the slide is on the first page. It is not changing. While we are looking from here, it is still in the first page.
Okay.
Can you, could you please share your entire screen? There is a share option. Then
I'll share everything and we'll see.
Yeah.
Can you now see?
Yes, now it is changing. You can make it the presentation mode, sir.
Okay.
Thank you. Thank
Okay,
you.
so I'll just show you. Yeah. Okay. So I'll try to not to use too much time then. But so I was showing this is the array, and this is the element that we came up with to generate circular polarization at the 2 frequency, and we basically excite the element on the bottom left corner of the element itself. And the post is actually located in this area where we actually use these posts to maintain this the distance between the patch element and the ground plane, but also to help us generate the circular polarization, because otherwise, with a half E-shape element, you would not be able to generate circular polarization with this shape. And so this is the subarray. 8x8 element that we first fabricated and tested to demonstrate the concept. And as you can see, the agreement between calculation and measurements in terms of reflection coefficient and radiation pattern are in excellent agreement. But most importantly, the aperture efficiency was satisfied. It is more than 80% efficiency. So then here, I was showing the comparison with the other antenna, which all have less than 50% efficiency. So this is the radial line slot array, and here this is the antenna that we use on the Curiosity rover and also on the Ingenuity rover, the latest that we actually sent. And so although these arrays are quite small, the aperture efficiency was very, very small. And that's the reason why people thought it was impossible to achieve more than 80% efficiency. And we did it with this antenna. Oh, and so as a result, the mass was drastically reduced, and also the half power beam width was increased, which allows us to relax the pointing requirements, which from a system point of view, it helps a lot. So this is the 16x16 patch array, which consists of 2x2 subarrays that I was showing earlier, and they're all fed with a waveguide. So as you can see on the back of the array, we have a waveguide power splitter on 1 to 4, and that allows us to maintain the aperture efficiency that we needed. And we tested this antenna across a very large temperature range. So most importantly, most of the time we will be at cryogenic temperature, so on the very cold end, minus 170 C, and we verified that the performance are not being impacted because this antenna was designed to do so, because it's made all of mainly of metal, so you only have the CTA mismatch. So at cold you will have the antenna will shrink because of the coefficient thermal expansion. So this is the lander itself that will land on the surface of Europa. And what I was saying is that one of the critical requirements is that the antenna needs to be folded atop of the surface of the lander because of the landing vehicle that will be right on top of the lander itself. And that's the reason why we couldn't use a reflector antenna. And that's the reason why we had to come up with a flat antenna that was highly efficient. And this is where this antenna saved the day. And this is the final antenna. So this is actually a 85 centimeter by 85 centimeter array that will be folded on top of the surface of the lander. We've tested also across a wide range of temperature, and we also did vibration, shock, and acoustic. Actually, acoustic is very critical for very large antennas. So we had to do this test on this antenna. And as you can see, the agreement between calculation and measurement is also quite outstanding. And this is a picture of the lander prototype that was fabricated for a landing test. So as you can see, the landing gear legs that are here, they were developed specifically to be able to land on any surface, because we don't know what the surface will look like on Europa. We had to come up with a solution to land on any type of surface, whether it's flat or completely random. This lander will be able to land on any surface thanks to our mechanical colleagues who came up with these landing gears. And so we placed the antenna on top of the lander itself, I mean the mock-up, in order to have a good visualization of what the lander will look like. And so you can see that the antenna itself is as big as the body of the lander. So now I'm going to talk about another missions, which was quite exciting. If you're following space exploration, obviously everyone has heard of the Mars helicopter, which was the first powered flight in another planet. So it was quite a feat. Initially, this was supposed to be only a technology demonstration, which exceeded any expectation. It was supposed to perform a maximum of 5 flights and survive a mission life of only 30 days. A year later, we're still working on it. It's still surviving. It's still operating on the surface of Mars. And not only it is now part of the rover mission, which the helicopter is actively being used to actually scout around the rover to find spots that the rover would be interested in studying. So it takes pictures of areas that are very, very difficult for the rover to access, and you will see why it's very. So as you guys all know, we have a few orbiters that are capable of taking very good images of the surface of Mars. Actually, we have a map of Mars. You can actually find that on the equivalent of Google Earth, but Google Mars, where you can actually actively move around Mars and look at different areas of Mars. So I invite you to do that if you're curious. But here I wanted to show you an example of pictures that we're capable of taking from these orbiters. The orbiters that will be at an altitude of 200 miles. We are not capable of detecting very, very fine features on the surface of Mars that will allow us to decide where the rover should go. And that's where the helicopter comes very handy. This is the kind of pictures that the rover is capable of taking. So if you were interested in going into this crater with the rover, you would have to move the rover itself very, very close to the edge of the crater. And you will take the risk of being exposed to that kind of rocks that can actually break the wheels of the rover itself. So if you do that, if you didn't have to do that, you would try to avoid to do that. So here is actually a very, very interesting map, because the scientists were interested in going into this crater, and they spent more than 100 days roaming the perimeter of the crater in search of an entry point, and they couldn't do so. So they wasted a lot of time. And just to give you an idea of how much time they wasted, the mission life of Opportunity was supposed to be only 90 days. So it's more than the mission life of the rover itself, which is significant. So after wasting all this time, not only they wasted a lot of time, they also damaged the wheels quite significantly. This is an example of damages that we've seen on Curiosity rover, and that's the reason why we want to avoid doing that in the future. And that's the reason why the helicopter comes handy, because now the helicopter can do all the dirty work in spite of having the rover doing that. And also another feature that that the helicopter can bring on the table is the fact that it can go in areas where a rover will not be able to go. And here is an example of it. Obviously, you will not be able to go in such a risky zone because you will take the risk of breaking the rover and fall off the cliff. So I'm going to skip through that, but just to summarize very quickly, I think most of you know that flying on the surface of Mars is very complex. First, because the density on Mars, the atmosphere of Mars is only 1% of the density of Earth's density. And so obviously it makes producing lift complex. Although you might think that the gravity might help, it's only 2/3 of the gravity of Earth, so it doesn't compensate this difference in terms of density. So we had to come up with a design that's light enough and that could generate enough lift to fly on the surface of Mars. So it was a trade in terms of power available that's provided the solar panel that you see on the surface of the helicopter. And obviously you cannot make that as large as possible because then you will increase the mass quite significantly. And it's also a trade of the size of the blades because you want these blades to be as large as possible, but you're also limited in terms of storage volume on the belly of the rover because this helicopter was folded on the belly of the rover. And then there is also the capability of the rotation speed of the blades. You want them to be as fast as possible, but at the same time, you cannot exceed the Mach speed limits on Mars, which is different than the one on Earth. So you have to take all of this into account and come up with the optimum design to do that. So the impact on the engineers like me, who were responsible of delivering flight hardware, is the fact that we have very limited power allocation and also mass allocation. So we had to come up with my team, which was we were delivering the telecom subsystem. We were given only 14 grams to communicate at a distance of up to 1 kilometer on the surface of Mars. And most of the communication is being done while we are on the ground, landed. And that makes it much harder because the path loss are much higher on the ground as opposed to when you fly where it's closer to free space, free space attenuation. For the antennas, we actually naturally used a monopole. So on the helicopter, that's this tiny monopole that you see here that was, I think the mass was less than 2 grams, including the connector. And it had to be extremely robust because obviously you're exposed to a vibration during launch, you're exposed to shock during the landing on the surface of Mars, and you're also exposed of the temperature swing during the cold night on Mars and during the hot during the days. And so this is the antenna we came up with, which was actually fairly simple to put together and extremely robust and survive all of these constraints that I just enumerated. And we use the solar panel as a ground plane. And as a result, this is rectangular shape. You will have asymmetry on the cross polarization, which is what you see here. And that's why we don't have a cross polarization that's perfectly flat and low. This is due to the shape of the ground plane itself. And on top of that, you have the blades. The blades are made of carbon fiber, a very thin layer of carbon fiber filled with foam, because they need to be extremely lightweight. I usually say that the first time they put these blades on my hands, they told me to close my eyes, and I barely realized that I was carrying something because of the cold that I felt on my hand. Otherwise, the mass is, you barely actually can feel the difference in terms of mass. So it's quite impressive how they actually manage to keep these blades very, very light. But as the blades are rotating, because it's made of carbon fiber is a very, very good reflective surface at 900 megahertz, which is the frequency of operation for our radio. And as you can see, as the blades are rotating, the cross polarization is being affected, and that has an impact on the polarization loss. And so you have to take that into account when you make your predicts. This is the monopole that we used on the rover. Unfortunately, we were given the worst location on the rover and a very tiny ground plane, so the performance of the antenna were very crummy. And as a result, we had to live with it, and we had no other options, so we had to live with it, and we had to predict our link based on this very poor performance on the rover side. So this is the link that we would get once we're landing. So there is 3 cases, which is the base cases. All of that is probabilistic. Whenever we do a link budget, it's always probabilistic. In the center is the average case, and on the far right is the worst case, when you have the worst alignments, where you have the cross pole and the co-pole of the helicopter antenna that are you have an XPD that's basically equal to 0. So you have very, very high polarization loss. It is basically the polarization loss that impacts the difference between each of these link cases. So in dark green, it's actually we can achieve 250 kilobit per second. Light green, it's 20 kilobit per second, and obviously in white, you will lose communication completely. So in most, be able to have 1 kilometer coverage around the rover, which is what we were requested to achieve. And once we fly, we don't have any problem anymore. You will be able to close the link at highest data rates most of the time. So this is not the case that worries us. It was mostly when we're landing. By the way, you have a very nice picture of the flight helicopter on the left. You can see the antenna in the center, the solar panel, the blades. So as you can see, it's a coaxial helicopter. And on the bottom, you have this tiny box where we have all the electronics in there, and we have heaters to keep it warm during the very cold nights. And you have the landing legs. We have a total of 4 to make sure that we don't crash during each landing. So we did a lot of tests. We had these mock-ups for the rover itself and the helicopter itself, and we put together these measurements. We separated them by a distance of 250 meters, and we verified that our predicts actually match. So you can see the structure on the bottom. We were actually manually turning the rover around to actually do different measurements around the rover. So you can similarly, it's very similar to an antenna radiation pattern measurement, except that there is a lot of other factors that you have to account for here. So you cannot have as good as of an accuracy, but that's much more closer to the reality. So that's why we push to actually do a field test, as opposed to spending an insane amount of money to do a very highly accurate antenna radiation pattern that will not really give us the answer that we wanted. So then, once we were on Mars, we achieved several flights. This is the first flight where we actually flew at an altitude of 3 meters, and we hovered around for like 30 seconds and then landing back on the same spot. And those are the predicts using our link predicts. This is so basically in our link, we always take into account the antenna radiation pattern and the polarization loss that we get from that. And those are the predictions that we had. So you can between calculation and measurement, we had a very good agreements. So this is when we were before taking off, while we were hovering around at 3 meters, and this is after landing here. And you can see we have very, very good accuracy. So that gives us a very good confidence moving forward with our link prediction. So then this is flight number 4, and here I'm showing coming from point B to A, going back on the same spot. And those are the received power as we were moving around. And as you can see, again, the calculation and the measurement on Mars, which is basically given us by the radio, are in very good agreements. Flight 5, same thing. Here we started at a distance of 92 meters from the rover, and we went to a distance of 128 meters. And same thing here, we're showing as the helicopter is moving around, we're showing the received power, which is also in very good agreements. Here's the problem that came up though. After 30 days, which we didn't expect that, but NASA decided to extend the Mars helicopter mission, and we were all very excited about it. But then all the work that we did was no longer applicable because all of the link budgets that we derived were only meant to be used when we had a line of sight between the rover and the helicopter and a fairly flat surface between the two. But as the time passed, the rover started moving around, going very far away. The helicopter team started to be adventurous some areas to venture and to study and take images. And in a lot of cases, line of sights were no longer satisfied. And so they still continued using these predicts, knowing that they were not accurate, until they lost communication completely, or at least not lost communication, but the predicts were too far off that they realized that there was a potential of losing the helicopter asset on Mars. And so they came back to me and they asked me if we could come up with a better solution, better predicts. And we decided to use the WinProp tool, which is part of the Altair suite. I think most of you know Altair through the FECO software. And they have this tool that allows you to import the surface topology and to actually predict polarization, to predict a loss from a transmitter and a receiver. So we simulated the rover and the helicopter on FECO to include the radiation pattern of the rover and the helicopter. And we also found a way to export the surface topology of Mars and include it in the tool. We verified the accuracy of the tool through 18 available flights at the time to convince ourselves that the results were accurate enough. And we elected to use the parabolic equation, which accounts for the properties of the ground, conductivity and dielectric permittivity of the ground, and accounts for reflection, diffraction, and forward scattering as well. And the predicts came out quite accurate, so we decided to move forward and use this tool. And I'll show you a few examples. By the way, I think everyone, most of you knows CJ, who was actually very, very helpful in infusing this tool into our portfolio. And they provided support to actually make sure that we understood how the tool worked and all the numerical limitations of the tool as well, so we could use and apply this tool into our flight cases. So here, flight 18, which was the first one that we actually used the tool for. You can see on the left, you actually have the map, which we use for the operation team use. So you can see on the bottom, we have the rover and we have the flight path where we have the helicopter takeoff and the helicopter touchdown. And so the team tell us, this is where we're taking off, this is where we're planning to land. The rover will be located there, it might move in another location, and they're asking us to make sure that when the helicopter communicates with the rover, we're still able to communicate. And this is what we've done. So we know that we need at least a receive stressor of minus 105 dBm to be able to close the link. That's the constraint that we use when we are giving the answer to the ops team. And you can see that the accuracy between calculation and memory is outstanding. So we're less than 3 dB difference between the two, which is quite outstanding. And what you see here is where you have like a very red area is where the transmitter is located. So here is before taking off, and on the right, the map is after taking off, so after landing. This is the communication links that we will be able to maintain. And you can see that the rover is starting to be in an area where the signal is weak, but it was still high enough to be able to close the link. And the second case where after landing, we were already at a 500 meter, which is starting to be quite significant. This is the second case here. I'm just gonna scan through that, but you can see again, the accuracy between calculation and measurement is quite outstanding. And before I move forward, what I wanted to say here in this flight 28, by the way, flight 28, we were supposed to do only 5 flights. So we have totally achieved and exceeded any expectations. And as you can see here, we went past the 1 kilometer requirement and we were able to close the link at 1.4 kilometer, but it was in an area where we actually predicted that because the rover is located very high. So less surface losses. Let's put it that way. So the multipass contribution, so the reflection between the transmitter, the ground to the rover is much less significant when you're very high up a cliff. So that's the reason why we were able to communicate as very, but we were able to predict that ahead of time. And as you can see, we still have plenty of margin. So in cases like that, we're able to go even farther if we wanted. So now I'm going to switch gear and talk about CubeSat antennas. So first, I invite you all to look at the book that was published in, I think, early 21, I believe, published by Ieee. The title of the book is CubeSat Antenna Design. It covers a very wide range of missions and antenna design that was developed at JPL. So I invite you all to take a look at it. Here is an overview on how we actually typically pick high gain antennas for small satellite or CubeSats. There is 2 types of high gain antennas. The first one that you see on the left is the type of antennas that we use when we don't have a lot of storage volume, which are patch arrays that will be against the surface of the bus of the CubeSat itself. Deployable reflector arrays that can fold atop the surface of the CubeSat, and also meta-surface antennas where we can basically just put that against the surface of the bus as well. And then on the right side, if you have a lot of storage volume, then you can start looking at different type of antennas, like inflatable antennas, membrane deployable antennas, much larger reflector arrays antennas, mesh deployable parabolic reflectors, and slot arrays if you were interested in going at higher frequencies, higher than Ka band. So I invite you to take a look at this publication where there is much more details on this topic. Here is an example of patch arrays or even single patch that we use on almost every single deep space CubeSat. We have, I think, more than 8 that are planned to flight with Artemis on Orion. And this one is one of the CubeSat that I like a lot, which is called Neo Scout, that in the center has a solar, how do we call that? A solar cell that will allow us to use the sun to actually move to our destination. So that's actually very interesting. I invite you to read about it. This is the first time that we will ever use a solar cell on a CubeSat. Obviously, there is not a lot of deep space CubeSat. The only one I know of is actually Marco, Mars Cube one, which I also worked on. Here we actually have a patch array, 8x8 patch array, circularly polarized, that's on top of the solar cell panel, which is, again, carbon fiber, where the solar cell are populated on. And here, instead of populated this carbon fiber fixture with solar cell all around, we decided to use a fraction of it to put a deployable patch array antenna. And then we also have patch arrays on each side of it, which allows us to get full coverage. So you have on each side, they can do a plus minus 90 degrees, sorry. So regardless of the orientation of the CubeSat, we will always be able to transmit and receive at low data rates. And that's a feature that all of these patch that I designed are being used on every single interplanetary CubeSat, and they were also flown on Marco and demonstrated on Marco. So I'm going to talk about mesh deployable reflector antennas, and the first one is the one that we've flown on RainCube. This one is a deployable Cassegrain mesh reflector. As you can see, it folds into a very tiny canister of 10 by 10 by 15 centimeter, which is very, very small. And it deploys into a 0.5 meter parabolic reflector. Provides more than 50% efficiency, which is comparable to a lot of the Cassegrain non-deployable antenna that you can commercially buy. So we actually achieve very good performance at K-band. And I'm going to show you the deployment itself. So in black, it is the canister that you see. It's using a 4-screw system that push out the entire antenna out. And from that point here, there is no way back. Meaning that if you decided to fold back using the motorized 4 screws, you will not be able to come back. However, until this point, you're still able to fold again. So if there, for any reason, we are aware of a mechanical issue and we want to unstuck something, we'll be able to do that. But after that, there is no way to come back. It's uncontrolled, and you can see it with the deployment. And then we have the sub-reflector that's pushed out with this spring in the center. And the spring has enough force to ensure that it's pushed out against the hard stop on the tip of the horn. And we've done a lot of deployment to demonstrate that it can reliably deploy over and over and over. And once we convince ourselves that things are reliable enough, and we've done tests in vacuum as well, at cold and at hot, we decided that the antenna was fully qualified to go in space, which we did. And let me see, which we did, and here is the deployments. And initially, the reason why we actually took this video, which basically is just a bunch of images that we took, it was to verify that the antenna deployed successfully. So here you can actually see the feed in the center with the sub-reflector, the 4 struts that hold the sub-reflector, the top of the horn as well, and you can see the mesh as well here. So, and you can see the mid hinges in the center here. So then here's the first science that we actually collected. And the science that we collected was from this typhoon here, the typhoon Tami. This is the way the scientists called it. And here we actually did two types of measurements. There was two CubeSats that actually flew over this typhoon, 5 minutes apart, and they managed to, the scientists overlap the result of the two, and they were actually quite amazed with the good correlation between the two results that they obtained. They were so impressed and so excited about these two results. One is obtained with a radiometer, and the second one that you see, the vertical line, was obtained with RainCube using our antenna. And so we worked on a new mission that will allow us to do that. So let me skip through that because I think I'm running. I don't have a lot of time. So this is the mission that we proposed not too long ago, where we wanted to use this radiometer that I was mentioning, along with the RainCube radar itself. So the radiometer is actually here. Basically, you can see it. It's more or less the CubeSat itself that's being placed here. And here is the RainCube radar, which is located behind the boom that holds the feed, and the very large deployable reflector here. So this large deployable reflector was developed by Tendeg. So Tendeg initially started working on this concept for 1 meter deployable antenna. But when we started working on that with Tendeg, we asked them to ensure that this concept could be scaled to larger reflector if we wanted to use that on a small satellite instead of a CubeSat, which is what we ended up doing here. So in this mission that we proposed a year ago, we decided to use, I think it's a 1.6 meter reflector, along with 5 feet horn. And you will see why we're using these 5 feet horns. And that's where the innovation is, that's where the cleverness of the antenna engineers along with the radar engineers came to play. So if you use the spacecraft direction, the spacecraft movement, you will be able to achieve 3 dB beam width between each of the beam of this feed horn. But in reality, you don't have 3 dB beam width overlap. So the one that the black and red circle that you see are the 3 and 5 dB beam width. And if you cross in this direction, you can see that actually you achieve 3 dB beam width overlap between each of these beams. But in reality, from one beam to another, you have much more than 3 dB beam width, so you have very good isolation between each of the feed. But if you use the motion of the spacecraft itself, the footprint at the ground will allow us to achieve this 3 dB beam width overlap. So it's not very clear when I say that, so I put this doodle and animation together. So on the left, you have the spacecraft itself, and as the spacecraft will move, this is what will happen. So on the right, what you had on the right is the footprint that you have when you're not moving, right? That's the footprint that you're getting. And then as you move, this is the footprint that you're getting, and you can see that's how you're getting the 3 dB beam width overlap. And so then when they play with the timing between each of the pulse, they can actually act as if they had a real 3 dB beam width overlap. So there was by the way, this mission was funded, and we're now working actively on this mission. So we're very excited about it. So that's how a technology demonstration again turned into a real flight mission that will generate very, very useful science in the future. So this was another concept that was not yet selected, but that we came up with. So the scientists came, and the radar folks came to me and told me, hey, we want to use these flat satellites that you can see here. They're very, very flat. Those were developed by SpaceX to launch a very large constellation. And SpaceX is also making these flat sats available to the scientist community if we wanted to include science payload into them. And that's what we try to achieve with it, which will allow us to reduce the cost of a mission if we were able to do that. So the radar folks came to me and they told me, so here we have this concept where we want to use two different antennas. We need to have a beam overlap between these two different antennas. But here's the problem. We cannot include two antennas that are exactly the same. So we will have a Cassegrain antenna that will be a solid reflector. This is this one. And you need to come up with a way to use an offset deployable reflector so that we can fold that one and it doesn't take a lot of space. But they need to have the same radiation pattern, same footprint on the ground. Is that even feasible? So at first, thinking about it, knowing that the optics is not the same, I thought it would be difficult, but it's not impossible. And so we had to develop a lot of I wouldn't say tools, but methodology to actually optimize these designs to get the same beam overlap using two different optics, and that's what we achieved. So you can see here, you have a Cassegrain with 1, 2, 3, 4, 5, 6, 7 beam. Each of these beam, using the same principle as before, will provide a 1.5 dB beam width overlap. And then in the center here on the solid reflector, we'll have a W band horn as well. This is what you see in the center, and that's why the footprint is much smaller. And then on the right, we have this offset mesh reflector, and yet you can see that the beam overlap are perfect. That's perfect. They are very, very good. The pointing is good, and the beam width is nearly identical. And that's what you see between the solid lines and the dashed lines. That was very exciting work to do for me as an antenna engineer. It was super interesting. So then we've been working very actively on metasurface antennas, and I'll close on this topic, I believe. David Gonzalez, who's now he has a tenure position at the University of Rennes as a CNRS researcher. He was a postdoc at JPL and worked with me and Gautam on Gautam Chattopadhyay, that I'm sure a lot of you knows. We worked on these metasurface antenna that are made entirely of metal, and they are also 3D printed. And the reason why we wanted that is that we wanted to be able to use these antennas on any type of environment, any planets in deep space. We wanted to have these extremely robust antennas that could be efficient and operate up to Ka band. And thinking that in the future, if 3D printing additive manufacturing improves, we might be even able to push the limits to W band, which we're not yet there, but maybe in the future we'll be able to get there. So I invite you to take a look at this publication from David and all of the principles to achieve these highly directive antennas using these elliptical elements are details. And as you can see here, we achieve about 32 dBi of gain, dBiC, by the way, it's circularly polarized. It's one of the reasons why I like these antennas, that you don't need a polarizer. So they are completely flat. You excite them at the center of the antenna using a waveguide, and you get circular polarization. So if you are starving for volume and storage volume, then these antennas come very handy. We were not satisfied with the efficiency we're getting with these antennas. We were also not satisfied with the accuracy of the fabrication. So we did two things. We worked on improving the efficiency, and we managed to get on this prototype 50% efficiency. Since then, we actually improved the design to now achieve more than 70% efficiency with such antennas. But here I wanted to show this design though, because we fabricated it and tested it, and we actually improved the fabrication. So if you compare this design here, you can see the roughness of the element, which is not great. And this one, which is much better. It's because we actually did some EDM after that to actually flatten the top of these elements. And that improved the accuracy between calculation and measurement very significantly. So now we can say very accurately, very confidently that we can fabricate these antennas very accurately. They are very cheap. You can make a lot of them very quickly. And here is a demonstration. So imagine if you wanted to use these antennas on the large constellation that SpaceX are flying, for example. Let's say you're interested in flying 100 of satellites all the same. Well, that's a good way to actually expedite the fabrication of your antennas. So that's where these antennas comes very, very, very useful, and I think will bring a lot of values in these large constellations that the new space is extremely interested in it. So this is another metasurface antenna we've been working on. So one of my a friend who's a CMOS designer, Adrian Tang, has been working on this system-on-chip radar where he's generating. So as you can see, there is a transmitter here with an external power amplifier that excites one port of the antenna. And then another port of the antenna, which is the receive port, is connected to the receive pass. And to improve the isolation between the transmit and receive, he came up with this very neat technique to actually cancel out through his system on chip the isolation. So from, I think we start at 25 dBi, no, sorry. We start about 20 to 25 dB of isolation. He can improve that actively to 60 dB isolation, which allows the radar to be much more accurate. And so he initially told us that he needed 25 dB, 20 to 25 dB of isolation. And after we did a bunch of tests, we realized that we still need more isolation to get better science. But the first concept that we came up with is this one, where we have two horns, and they achieve the real 3 dB beam width overlap between the transmit and receive beam across a bandwidth of 6.5%. We achieved a minimum isolation of 20 dB. And I think the efficiency of this antenna was around 40 to 50% efficiency. I'm not quite sure. Don't quote me on that. Those are the calculation and measurement that we obtain. As you can see, this antenna is all made of metal, very simple to assemble together. Again, that allows us to build a lot of them very quickly. And this is the first test that we did. So this antenna was embedded on the radar itself. Let's see, did I have? No, I don't have a picture of the radar, but the radar is mounted behind the antenna. So that's what you see here. And all of that is mounted on this very large UAV. What I was talking about, the isolation, and this is what provides you the dynamic range that we needed. Here we achieve 45 dB of dynamic range on the radar, which we thought was good enough, but we're not satisfied enough. We still got very good science. So you can see the first test flight that was performed, and that was measuring, oh yeah, I forgot to mention, what we're doing here is snowpack measurement. So it's snow measurements. And here is one measurement that you see. So you can see the snow surface and the ground return here. So you can actually see that we can accurately say what the depth of the snow is thanks to these measurements. And what's amazing is the size of the radar itself. So actually, the weight is on the radar is mainly driven by the antenna, not by the radar itself. So it's quite amazing what Adrian has been able to achieve with his CMOS system on chip. So now we're building a second generation antenna that will provide more than 60 dB of isolation between the transmit and receive port. And next time around, we will be presenting that. We're extremely excited. Another thing that we've been working on was to increase the efficiency of these antennas, because we're not satisfied with 40%, and we want more than that. And we come up with a very good solution to do so. My postdoc, Dr. Gaurangi Gupta, who will be attending the conference in person, came up with a very neat technique to do so, and I'm sure we'll be presenting that in next conferences. So I'll just end this talk with a few references to some of my and my colleagues' journals that I invite you to take a look at, and some images of covers of either books or magazine that I invite you to read. Thank you very much. And if there is any question, I'll be happy to answer them now.
Thank you, Dr. Chahat. The floor is open for any questions. All right. Thank you, Dr. Chahat. Wonderful presentation. You quite literally took me on its journey out of this world, and we definitely have a lot to take away from this. And once again, on behalf of the organizing team and NIT Rourkela, huge thank you for your time and knowledge. And it's over to Annapurna. Thank you.
Thank you very much.
Thank you, Dr. Chair, and thank you, Vanita, for being with us. It was, Dr. Chair, it was a wonderful presentation. Thank you very much for being with us and being a part of Wams 2022. Any questions? We would like to take questions from the audience.
Good morning, Nazar. What is time there?
Good morning.
How are you?
Yes.
Very exciting talk and very informative talk as usual. Question is, I think all these technologies you used, I think first time I think people ever did, especially the metal patch, and people have been working on these patches for a long time. So nobody found a solution. Nobody found a solution like what you have to generate CT with a single feed point, and using all metal to get away from the ESD and other problems. So that's very good. And other things also, helicopter, I think first time, I think people ever flown a helicopter on Mars or any other planet. So all these things are first time in the industry. So you said the future is flat. So how flat and how big is going to be the future for you? So maybe I think in the introduction people didn't tell exactly. I think he's too modest to put his bio, but just want to tell that he became IEEE fellow at the age of 34. So youngest IEEE fellow ever, I think. So that shows how he works, and he's the engineer's engineer, I would call, all the time. So always on the mission, and he does research, but to the level where I think it's useful to the mission or to the hardware. At the end, of course, he's working with other people, mechanical manufacturing, and at the end, get your product delivered. So that's what makes another special compared to others. But you can tell me how flat it's going to be and how big the apertures are going to be.
Yeah, so I think you're referring to the title that I had on the meta-surface antennas, which I should be careful because I don't want people to think that Earth is flat. That's not the meaning of this title. What I meant by that is that we're trying to simplify the deployment of all these antennas. So I mentioned the deployable mesh reflector, offset mesh reflector, or even Cassegrain. They still remain quite complex and difficult for everyone around the world to actually apply this technology. I think the Europeans are still trying to develop this their own deployable mesh reflector. So it's not an easy technology to develop. So what we were hoping to do and still aiming to do is to use meta-surface antennas and to deploy them as membranes. And then in that case, you can deploy them, you can deploy this very large surface that you excite in the center. So you don't need to worry about deploying far away from the reflector itself. So that's where this meta-surface come handy. However, the larger the antennas are, these meta-surface antennas are, and the smaller the bandwidth will be. So that's also a trait that you need to be aware of and to be careful with. But you can also, there is a trade in terms of size, bandwidth, and efficiency. So you can make them large enough, increase the bandwidth, but it will be at the cost of efficiency. So those are the trades that you need to look at, and I think it really depends on the application, and you need to be careful of where to use this type of antenna technologies. For example, reflector rays. Reflector rays, people have been working on reflector rays for many years and never been really used commercially. And the first time we actually used these reflector rays was on the CubeSat, on Mars CubeSat, because we needed to deploy off of the surface of the CubeSat. We didn't have any storage volume inside of the CubeSat. And that's where these antenna technology that people started putting completely aside can very useful. So every antenna technology has weakness and strengths, and the role of the engineer is to use their strengths and weakness appropriately to infuse them accordingly to the right missions. Any other questions?
Thank you, Dr. Chair. I think there is no more question. Thank you for being patient and presenting a lot of things to us. So thank you, sir.
Thank you very much. Thank you for inviting me and having me here.
Thank you, everyone. Now I request everyone to proceed for the lunch at the South Guest House. Then we will meet around 3 p.m. today for the oral session.